Welcome to ZzZscience. Before we begin, allow your body to relax, your breathing to slow, and your mind to gently drift. Tonight, we explore science, quietly, calmly, and without urgency. There is nothing you need to do, only listen. Members every season, every rainfall, every root that has ever pressed downward in search of water and stability. This threshold is not a line, but a gradual becoming, an invitation written in moss and shadow. The air itself changes as you stand here. It is cooler, even on the warmest days, as if the forest breathes out a gentle exhalation that carries the scent of living wood and patient growth. Breathe it in slowly. There is no hurry here. There has never been hurry here. The forest has been breathing this way for centuries, long before you arrived, and it will continue long after you have returned to your other life. But for now, for this moment, you are here at the edge, and that is enough. Look ahead into the spaces between the trunks. The light here is different too. It does not arrive in the bold, unfiltered way it does in open spaces. Instead, it filters down through layers upon layers of leaves and branches, becoming softer, gentler, tinged with green and gold. This filtered light creates a kind of underwater world where everything moves slowly and deliberately, where shadows are not harsh but soft-edged and welcoming. Notice the quiet. It is not the absence of sound, but the presence of a different kind of music. Listen to how the silence holds space for the smallest whispers of life. Somewhere in the canopy above, a single leaf releases its grip on a twig and begins its spiral descent, turning slowly in air thick with the patience of ages. You cannot see it yet, but if you listen with more than your ears, you can sense its journey, the way it catches momentary currents, the way it surrenders to its path without resistance. The trees at this threshold are the greeters, the sentinels who stand between worlds. They are often the oldest, the most weathered, the ones whose bark has been textured by countless seasons of sun and rain and snow. Their trunks are thick, wider than your arms could ever reach around, and their roots rise slightly from the earth like the knuckles of ancient hands, gnarled and strong and absolutely certain of their place in this world. Touch one of these trees if you wish. Place your palm flat against the bark and feel the texture against your skin. It is rough, yes, but not in an unpleasant way. The ridges and valleys of the bark tell stories in a language older than words. This rough surface is protection, armor grown slowly year by year, a boundary between the vulnerable living wood inside and the world outside that carries wind and weather and the occasional wandering touch of creatures passing by. The bark is cool beneath your hand, even when the day is warm. This coolness speaks of the water that moves inside, the sap that rises and falls with the seasons, the life force that pulses so slowly you could never measure it with the impatient instruments of your usual world. If you could shrink yourself down and travel beneath this bark, you would find highways of fiber and vessel, tiny corridors where water and nutrients travel upward from the roots to the highest leaves, and where sugars created by sunlight travel downward to feed the reaching roots below. But we will not go inside yet. Not yet. For now, we remain here at the threshold, allowing the forest to recognize us, allowing ourselves to settle into its rhythm. There is wisdom in this pause, in this standing between worlds. The forest does not rush to reveal itself. It offers its secrets slowly, to those who learn to move at its pace, to those who remember how to be still. Around you, the threshold is marked by small things you might otherwise miss. There are tiny wildflowers growing at the base of the sentinel trees, their petals no larger than your smallest fingernail. They are white and delicate, growing in the liminal space where sunlight still reaches, but where the forest's influence has already begun. These flowers bloom without fanfare, without needing to be noticed, content in their quiet existence. Some are opening now, petals unfurling with a slowness that matches the turning of stars. Others have already completed their brief moment of flowering and are forming seeds, preparing for a future they will never see but trust completely. The moss grows here too, thick and impossibly soft. It covers stones and lower portions of tree trunks, creating small, verdant landscapes in miniature. This moss has no flowers, no seeds in the traditional sense, but it is no less alive, no less purposeful. It holds moisture like a tender memory, creating small, humid havens for even tinier creatures, beetles and spiders, and organisms so small they exist beyond the reach of your unaided sight. The moss is older than it looks, growing with such patience that its expansion is measured in years, not days. Some of these cushions of green have been growing for decades, adding microscopic layers to themselves with the dedication of ancient stonemasons building cathedrals grain by grain. Listen again to the quiet. It has depth, this silence. It has layers. There is the rustle of leaves overhead, so gentle it might be mistaken for your own breathing. There is the creak of wood, the sound of trunks and branches responding to the slightest breath of wind. A sound like an old house settling, comfortable and sure. And beneath it all, if you listen very carefully, there is the sound of growing, though it is too slow and too deep for your ears to truly capture. It is more a feeling than a sound, a sense of upward and outward movement that never stops, never rests, never doubts its direction. The shadows here at the threshold move so slowly you could watch for hours and barely notice their progress. As the sun travels its ancient path across the sky, the light shifts angle by tiny angle, and the shadows respond, sliding across the forest floor like gentle thoughts, like memories that surface and submerge without urgency. A root that was in full filtered light moments ago now finds itself in cool shade. A patch of moss that was shadowed begins to receive tiny particles of sunlight, each one a gift, each one transformed into the energy of life through processes too elegant and complex for us to fully comprehend. You are beginning to adjust now. Your eyes are learning to see in this gentler light. Your ears are tuning themselves to frequencies you had forgotten existed. Your skin is registering the different quality of air, cooler and richer and thick with the breath of 1,000 trees. Your heartbeat is slowing to match the pulse of this place, that deep underlying rhythm that measures time not in seconds but in seasons, not in minutes but in the expansion of growth rings hidden beneath bark. This is the threshold. This is where transformation begins. Not with drama or sudden revelation, but with gentle recognition. You are stepping out of the world of constant motion and into the world of constant presence. The forest does not go anywhere. It is always and completely here, rooted, present, alive in ways both obvious and invisible. Take one more breath at this threshold. Fill your lungs with this different air. Let your shoulders drop away from your ears. Let your jaw unclench. Let your thoughts begin to slow and space themselves out like the trees themselves, each one distinct, each one given room to exist without crowding its neighbors. Now, when you are ready, and there is no hurry, there is never hurry here, take your first step forward. Not a large step, but a small one. Feel how your foot meets the forest floor, how the decades of fallen leaves compress slightly beneath your weight, then spring back when you lift your foot for the next step. This ground is alive. This floor is breathing, and with each step you take, you are moving deeper into the secret life that has been unfolding here since long before you arrived. The threshold is behind you now. Ahead lies the forest interior, where the trees grow closer, where the light becomes even softer, where silence deepens into something like peace itself. But we will not rush toward it. We will walk slowly, we will notice everything, and we will let the forest reveal itself at its own pace, in its own time. For now, this is enough. You have crossed the threshold. You have begun the journey into stillness. Beneath your feet, beneath the soft carpet of decomposing leaves and the yielding earth, there exists an entire world you cannot see. This is the realm of roots, the underground cathedral where trees anchor themselves to existence, where they drink deeply from the earth's hidden reservoirs, where they communicate in chemical whispers that travel through darkness with patient certainty. To understand a tree, you must first understand that what you see above ground is only half. The story, perhaps less than half. For every branch that reaches towards sky and sunlight, there is a root that reaches downward and outward into soil and stone, seeking, always seeking, the elements of life. The roots are not merely anchors, though they are that. They are not merely straws drawing up water, though they do that too. They are explorers, diplomats, engineers, and architects, working ceaselessly in the darkness to support the visible majesty above. Imagine, if you will, that you could see through the earth as if it were glass. Imagine the forest floor becoming transparent beneath your gaze, revealing what lies hidden. What you would witness would take your breath away with its complexity, its artistry, its sheer patient determination. The roots spread outward in every direction, creating mirror images of the canopies above. But unlike branches that must compete for space with neighboring trees, roots interweave and overlap, creating a tapestry of underground connection that defies the apparent separation of individual trees. Where one tree's roots end and another's begin becomes a question without a clear answer. For in the darkness beneath the forest, boundaries blur and merge. The largest roots, the ones that emerge from the base of the trunk and plunge downward and outward, are as thick as your leg, sometimes thicker. These are the structural roots, the primary anchors that prevent a tree weighing many tons from toppling in wind and storm. They grow slowly, adding layers of woody tissue year after year, becoming denser, stronger, more deeply embedded in the earth's embrace. Some of these roots reach down 10 feet, 20 feet, deeper still, in search of stable ground and permanent moisture. They navigate around boulders, through clay, into sand and loam, reading the earth through touch and chemical sense, adjusting their path to find the most favorable route. But the structural roots are only the beginning. From these main thoroughfares branch countless smaller roots, and from those branch even smaller ones, creating a network of exponentially increasing complexity. Follow one of these roots as it grows thinner, divides, grows thinner still. Watch as it splits again and again, becoming as fine as thread, then as fine as hair, then finer still, until at last you reach the root tips, the growing points, and here you discover something miraculous. At the very tip of each tiny rootlet, there is a root cap, a cluster of cells that sense gravity and guide the root's downward growth. Behind this cap lies the zone of elongation, where cells stretch and multiply, pushing the root forward through the soil, particle by particle, millimeter by millimeter. It is slow work, this underground expansion, but it never ceases. Even now, as you stand in the forest breathing slowly, beneath your feet millions upon millions of root tips are pressing forward, growing, exploring, expanding the tree's reach into the earth. And here is where the story becomes even more extraordinary. Those finest root tips, those gossamer threads of living tissue, are not alone in their work. They have formed partnerships, alliances with other forms of life, so ancient and so successful that neither partner could thrive without the other. These partnerships are with fungi, with the hidden threads called mycelium that weave through the soil like nature's own internet, connecting tree to tree, forest to forest, in a web of communication and exchange that scientists are only beginning to understand. The fungal threads, hyphae they are called, are far thinner than even the finest roots. They are microscopic, invisible to your unaided eye. But collectively, they form networks of staggering extent. A single cubic inch of healthy forest soil might contain miles of these fungal threads, miles compressed into a space smaller than a child's block. And all of it alive, all of it busy with the work of connection and exchange. Where root meets fungus, something remarkable occurs. The fungal threads wrap around the root tips, sometimes penetrating between the root cells, sometimes forming a delicate sheath. Through this intimate connection, the tree and the fungus exchange gifts. The tree, which can perform the magic of photosynthesis in its leaves far above, shares the sugars it creates from sunlight, feeding the fungi that cannot make their own food. In return, the fungi, which can reach into spaces too small for roots to penetrate, gather water and minerals, phosphorus, nitrogen, trace elements, and pass these nutrients to the tree. But the exchange is more than nutritional. The mycelial network acts as a communication system, carrying chemical signals from tree to tree. When one tree is attacked by insects, it can send warning signals through this underground network, allowing its neighbors to prepare their defenses, to produce compounds that make their leaves less palatable, to call in predator insects that will feed on the attackers. The forest, which appears to be a collection of individual trees, is in truth a superorganism, connected and communicating, responding collectively to threats and opportunities. There is no malice in this system, no competition in the way you might imagine it. Yes, trees grow toward light and spread their roots toward resources, but they do so in a manner that allows for coexistence, for cooperation. Mother trees, the oldest and largest in the forest, have been found to nurture their offspring and even the young of neighboring trees, sharing resources through the fungal network, giving freely of their excess to help the next generation establish itself. The forest takes care of its own. In the darkness of the soil, roots encounter obstacles constantly. A stone blocks the path forward. The root does not fight the stone, does not attempt to break through it. Instead, it grows around, sensing the contours of the obstruction through touch and through the subtle chemistry of the minerals. The stone releases. The root divides, sending explorers left and right, seeking the path of least resistance, finding the gaps and crevices, and eventually reuniting on the other side of the obstacle, having transformed what could have been a barrier into merely a momentary challenge. Water is the constant obsession of roots. They grow toward it with unwavering dedication, sensing its presence through the way moisture affects the chemistry of the soil. In times of plenty, when rain has been generous and the earth is saturated, roots spread broadly but not deeply, content to gather what is easily available. But in times of drought, when the upper soil dries and hardens, the roots push deeper, following the water as it retreats downward, sometimes reaching extraordinary depths to find the water table that never dries, that ancient reservoir of liquid that has been filtered through stone and time. The finest roots, those hair-thin explorers at the frontier of the tree's underground reach, have a lifespan measured in weeks or months, not years. They grow, they absorb, they gather nutrients, and then they die, their tissues decomposing and enriching the very soil they grew through. They are replaced continuously by new root tips emerging from behind, an ongoing cycle of growth and death and renewal that happens invisibly, constantly, beneath every forest everywhere. A large tree might have millions of these fine root tips at any given moment, and over the course of a year, it might create and lose several complete generations of them, each generation contributing its substance to the improvement of the soil. The soil itself is transformed by this process. What was once mineral and sterile becomes rich with organic matter, becomes loose and crumbly, and able to hold both water and air in the spaces between particles. The roots create channels as they grow, and when they die and decompose, these channels remain, allowing water to infiltrate deeply, allowing air to reach buried layers, creating habitat for earthworms and insects and microscopic organisms, each adding their own contributions to the living soil. Some roots secrete substances, sugars, proteins, enzymes, that attract beneficial bacteria and other microorganisms. These tiny beings colonize the immediate vicinity of the root, the rhizosphere, creating a zone of intense biological activity where nutrients are transformed, where minerals are made available, where the chemical conditions are carefully maintained to favor the tree's needs. The root does not do this work alone. It creates conditions that encourage allies to gather, and in gathering, they form a community devoted to the success of the whole. In winter, when the visible forest appears to sleep, when branches are bare and no leaves catch the light, the roots continue their work. They grow more slowly, yes, but they do not stop. They cannot stop, for even in dormancy, the tree needs water, needs to maintain the internal pressures that prevent its cells from collapsing, needs to prepare for the explosive growth that will come with spring's return. The roots are patient. They know that every season passes, that what appears to be ending is merely transforming, that beneath the frozen surface, life persists and plans and gathers its strength for the renewal to come. There is a mathematics to root growth, though it is not a mathematics any human mind designed. The branching follows patterns that maximize coverage while minimizing the energy invested in creating root tissue. The angles of branching, the distances between splits, the thickness of each successive generation of smaller roots, all of this follows rules written in the tree's genetic code, refined over millions of years of evolution, tested by countless generations in the fierce laboratory of survival. And yet, for all this precision, there is also flexibility, responsiveness. If one direction proves rich in nutrients, the roots elaborate more extensively in that direction. If water is found to one side, growth skews to follow it. The tree is constantly sensing its underground environment, constantly adjusting its growth patterns to match what it encounters. This is intelligence of a sort, not conscious in the way you experience consciousness, but intelligent nonetheless. A distributed intelligence spread through millions of growing tips, each sensing, each responding, each contributing to decisions made by the organism as a whole. Deep in the earth, the oldest roots have been growing for decades, for centuries in some trees. They have witnessed the passage of seasons you cannot count, have survived droughts and floods, have felt the trembling of the earth itself during earthquakes and the heavy footfalls of animals long extinct. They persist, adding microscopic layers to their girth each year, becoming denser, more mineral-laden, more deeply integrated with the stone and soil around them. These ancient roots sometimes outlive the trees they supported. When a tree finally falls, claimed by age or lightning or the weight of too much snow, the roots may persist for years, slowly metabolizing their stored reserves, slowly being consumed by fungi and bacteria and beetles, slowly giving themselves back to the forest as food for the next generation. Even in death, they serve. Even in dissolution, they contribute. Above ground, you stand among the trunks, seeing only bark and branch. But now you know what lies beneath. Now you understand that you are standing not on solid earth, but on a living network, on the equivalent of countless miles of root and fungal thread, on a communication system that connects every tree you can see and thousands more beyond your sight. You are standing on the foundation of the forest, on the source of its stability, on the reason it can stand against wind and time. This is the language of roots, a language of chemistry and touch, of growth and adaptation, of cooperation and mutual support. It is a language spoken in darkness, translated through the medium of living soil, heard by partners you cannot see, but who are as essential to the forest as the trees themselves. The roots beneath you are reaching out right now at this very moment. They are growing, seeking, connecting. They are the hidden half of beauty, the underground cathedral that supports the visible temple of trunk and branch and leaf. And they are patient, so patient. They have all the time in the world. There is a miracle happening inside every tree around you, a miracle so quiet and so constant that it is easy to forget it is a miracle at all. It is the rising of water, the upward journey of moisture from the deepest roots to the highest leaves. Sometimes a distance of hundreds of feet, lifted without pump or engine, without noise or visible effort, rising in defiance of gravity through channels so narrow that a human hair would seem a vast tunnel by comparison. Stand close to one of the great trees now. Place your hand against its bark once more and consider what is happening just beneath your palm. Inside the wood, in thin vessels arranged in rings that mark the passage of years, water is ascending. It rises not in a rushing torrent, but in a patient, steady flow, molecule following molecule in an unbroken column that stretches from root tip to leaf edge. A column that never breaks, never fails, sustained by forces both physical and elegant. The journey begins in darkness, in those finest root hairs we visited in the last chapter. There, in the soil between particles of mineral and organic matter, water molecules cluster around root surfaces. The concentration of dissolved minerals inside the root cells is higher than in the surrounding soil, and this difference creates an osmotic pressure, a gentle but persistent pull that draws water across the cell membranes, into the root tissue, beginning the long ascent. From the root hairs, water moves inward through layers of cells, each one passing the precious liquid to its neighbor like a bucket brigade operating at the molecular scale. The water crosses membranes, flows through cell walls, moves through the spaces between cells, always inward, always toward the center of the root where the first true vessels await. Hollow tubes created from cells that lived, matured, and then died, leaving behind their woody walls as pipelines for the generations to come. These vessels, these xylem tubes, are marvels of natural engineering. They are narrow, sometimes only a few micrometers across, and their walls are reinforced with lignin, the compound that gives wood its strength. The narrowness is not a limitation, but a necessity, for it is the narrowness itself that allows water to rise to such heights. In a phenomenon called capillary action, water molecules, which are attracted both to each other and to the walls of the vessels they travel through, can climb upward against the pull of gravity, rising higher the narrower the dark tube. But capillary action alone cannot explain the full journey, especially not in the tallest trees. There is another force at work, a pull from above rather than a push from below. This force originates in the leaves, in the crown of the tree where sunlight meets chlorophyll and the business of photosynthesis proceeds. The leaves are hungry for water. They need it for photosynthesis, yes, but they also lose it constantly through tiny openings called stomata, pores in the leaf surface that must open to allow carbon dioxide to enter for photosynthesis. When these stomata open, water vapor escapes, diffusing out into the air in a process called transpiration. On a warm, sunny day, a single large tree might transpire hundreds of gallons of water, sending it invisibly into the atmosphere, creating a constant demand that pulls water upward through the entire length of the tree. This pulling force, this tension created by evaporation at the leaf surfaces, is transmitted downward through the continuous columns of water in the xylem vessels. Water molecules are cohesive. They cling to each other with hydrogen bonds, creating chains that resist breaking. When a molecule evaporates from a leaf, it pulls the molecule below it upward, which pulls the one below that upward, and so on, down and down through hundreds of feet of wood, all the way to the roots. It is like a rope made of water, strong in its continuity, functioning as long as the column remains unbroken. This is why the continuity of the water column is so vital. If air enters the vessels, through injury, through freezing, through extreme drought, it can create bubbles, embolisms that break the column and render that vessel useless for transport. The tree has strategies to work around such breaks, routing water through adjacent vessels, sometimes even repairing damaged ones. But the process is costly, the damage sometimes permanent. The water column is both strong and fragile, powerful and delicate, a paradox that defines its nature. Inside the trunk, the xylem vessels run vertically, parallel to each other, bundled together in the growth rings you would see if you could cut through the bark and into the wood. The newest vessels, formed just this year in a layer called the cambium, are smooth and efficient, open and ready. Older vessels, from years past, may still function, or may have become blocked or filled with resins and other substances, retired from active service, but still contributing structure and strength to the tree. The water that rises through these vessels is not pure. It carries dissolved minerals, nitrogen, phosphorus, potassium, calcium, magnesium, iron, and trace elements, all the nutrients gathered by the roots from the soil. This dilute solution, this sap, is the tree's lifeblood, carrying not just hydration, but sustenance to every living cell in trunk, branch, twig, and leaf. The concentration is low, mostly water with just small amounts of dissolved minerals. But over days and weeks and months, enough nutrients are transported to build new wood, new leaves, new growth. The speed of this ascent varies with conditions. On a cool, humid day, when transpiration is low, the flow might be sluggish, barely moving. But on a hot, dry, windy day, when the leaves are losing water rapidly, the sap can flow at remarkable speeds, in some trees up to several feet per hour. It is still far slower than water flowing through human plumbing, but considering it is moving without any mechanical assistance, against gravity, through tubes narrower than you can see, it is extraordinary. Listen, if you can, to the sound of this water moving. You cannot, of course, not directly, for it is too quiet, too subtle for human ears. But in the spring, when the sap is rising with particular vigor, when trees are mobilizing stored sugars and pushing fluids upward to fuel the season's growth, there are those who say they can hear something, a whisper, a humming, a sense of movement within the wood. Whether this is true or merely wishful interpretation of other sounds, it speaks to our desire to connect with this hidden process, to witness the unseen miracle of rising water. The trunk itself is a study in layers, each with its own role in the water's journey. Outermost is the bark, protective and insulating, containing cells that are no longer alive, but still serving, still shielding the living layers within. Beneath the bark is the phloem, a separate system of vessels that carries sugars and other organic compounds downward from the leaves to feed the roots and lower portions of the tree. Then comes the cambium, a thin layer of actively dividing cells that creates new phloem on the outside and new xylem on the inside, slowly expanding the tree's girth year by year. And then the xylem itself, the sapwood and heartwood. The sapwood, lighter in color, is the active part, the living highway where water rises. The heartwood, darker and often denser, is the xylem that has aged beyond active transport, its vessels filled with resins and extractives that make it more resistant to decay. The heartwood provides structural strength, but no longer participates in moving water. It is the tree's historical record, its accumulated past, still supporting, but no longer transporting. In some trees, you can see evidence of this water transport in the patterns of the wood grain. The vessels in hardwoods like oak and ash are large enough to be visible as pores when the wood is cut, arranged in rings or scattered patterns, depending on the species. In spring, many trees produce vessels that are wider and more numerous to take advantage of the season's abundant water and to support the flush of new growth. In summer and fall, the vessels formed are narrower, denser, creating the darker portions of each growth ring. The alternation of spring wood and summer wood creates the ring pattern that allows us to count a tree's age, each ring a calendar entry, a record of 1 year's journey around the sun. The water that rises through these vessels will eventually reach the branches, flowing from the main trunk into increasingly smaller divisions. At each junction, the flow divides, some water continuing upward into higher branches, some turning aside into lateral branches that spread outward. The principle remains the same: continuous columns of water pulled upward by evaporation at the leaves, maintained by the cohesion of water molecules to each other and their adhesion to the vessel walls. As the branches divide and subdivide, becoming twigs, then becoming the tiny stems that hold individual leaves, the vessels become correspondingly smaller, the flow divided among countless parallel paths. A single leaf at the end of its stem receives water that has traveled the full height of the tree, possibly passing through dozens of cell layers and hundreds of feet of xylem vessels, arriving at last at its destination, ready to serve. In the leaf, the water enters the cells that perform photosynthesis, providing the hydrogen atoms that will be combined with carbon dioxide to create sugars. But most of the water that enters a leaf never participates in photosynthesis directly. Instead, it evaporates through the stomata, returning to the atmosphere, completing a cycle that begins with rain falling on the forest, soaking into the soil, being absorbed by roots, rising through the tree, and returning to the air from which it originally condensed. This cycle connects the tree to the atmosphere and to the water cycle of the entire planet. The moisture transpired by forests contributes to cloud formation, to rainfall downwind, to the regulation of local and regional climates. A forest is not merely a collection of trees, but a climate-making entity, a living system that participates in the hydrological cycle at a scale that affects everything around it. On cold nights, especially as winter approaches in temperate forests, the water in the xylem vessels faces a new challenge. Water expands when it freezes, and if it were to freeze inside the narrow vessels, it could rupture them, destroying the tree's water transport system. Different trees have different strategies to survive freezing. Some allow their xylem to freeze, but do so in ways that prevent damage, forming ice crystals in safe locations. Others concentrate sugars and other compounds in their sap, lowering its freezing point like natural antifreeze. Still others, particularly evergreens, maintain such narrow vessels that the water in them remains liquid, even well below the normal freezing point, held in a supercooled state by the surface tension in the tiny tubes. When spring returns, when the soil thaws and temperatures rise, the water begins to flow again with renewed vigor. In maple trees and others, the freeze-thaw cycle of early spring creates pressure changes that cause sap to flow outward from wounds, the phenomenon that allows maple syrup producers to harvest their sweet sap. This is a temporary condition, a result of the tree mobilizing stored sugars and preparing for the growing season, and it demonstrates the dynamic nature of the water transport system, not a passive series of tubes, but a responsive network that changes its behavior with the seasons. The rising of water is continuous, relentless, patient. It does not stop at night, though it may slow. It does not cease in winter, though it may reduce to a bare minimum. As long as the tree lives, water rises, carrying life from root to leaf, connecting earth to sky through the medium of wood and sap and molecular attraction. Stand here in the forest, in the presence of these trees, and know that inside each trunk, inside every branch and twig, water is rising right now. Hundreds of gallons per day in the largest trees, all moving silently, efficiently, powered by evaporation and molecular cohesion, sustained by the tree's perfect integration of physical laws and biological necessity. It is a miracle made mundane by its constancy, made no less miraculous by being understood. The water rises. It has always risen. It will rise tomorrow and the day after, year after year, decade after decade, as long as the tree stands and the rain falls and the sun warms the leaves. It is the fundamental flow of the forest, the river running vertically through wood, connecting depth to height, darkness to light, earth to air. And it is happening all around you, invisible and essential, quiet and profound. The rising of water through the secret passages of the trees. Touch the bark again now. Let your fingertips explore its surface with new attention, new curiosity. What you are feeling is not dead tissue, though that is what many believe. Bark is not simply a shell, not merely a rough exterior protecting the vulnerable wood within. It is architecture, it is history, it is the tree's living interface with the world, and it has stories written into every ridge and furrow, every flake and scale, every textured inch of its surface. Each species of tree creates its own distinctive bark, as unique and recognizable as a face. The smooth silver grey of beech, the white papery layers of birch, the deeply furrowed darkness of oak, the puzzle piece plates of pine, the shaggy strips of cedar. Each is a signature, an identity, a particular solution to the challenges of being a tree in a specific environment. To learn to read bark is to learn to know the forest's inhabitants by touch and sight, even in the depths of winter when leaves have fallen and other identifying features have retreated. The bark begins its life as something tender. In the youngest twigs, the outermost layer is often green, smooth, photosynthetic even, contributing to the tree's energy production while the leaves are still developing. But as the twig grows and thickens, becoming a branch, becoming eventually part of the trunk, the surface must change to accommodate the expansion of the wood within. The bark must grow as the tree grows, must stretch and adapt, and eventually crack or peel in patterns determined by the species and the stresses it encounters. The bark is composed of layers, like the tree itself. On the very outside is the outer bark, the roughened, often darkened tissue that you touch when you place your hand against the tree. This outer layer is composed of dead cells, their life work completed, their cell walls thickened and impregnated with compounds that resist decay and repel water. These dead cells accumulate year after year, building up the characteristic texture of each species. The thick, corky ridges, the peeling layers, the blocky plates. Just beneath this outer armor lies the inner bark, or phloem, and this is very much alive. The phloem is the tree's second circulatory system, companion to the xylem we explored in the last chapter. While xylem carries water and minerals upward from roots to leaves, phloem carries the products of photosynthesis, sugars, amino acids, hormones, downward from leaves to roots, and to all the growing tissues of the tree. The phloem is delicate, easily damaged, and the thick outer bark serves in part to protect it from injury, from the teeth of animals, from the heat of fire, from the desiccating effects of wind and sun. Between the inner bark and the wood lies the cambium, that miraculous thin layer of dividing cells we have mentioned before. The cambium is only a few cells thick, but it is the growth engine of the tree. Each year it produces new phloem cells toward the outside and new xylem. cells toward the inside, incrementally expanding the tree's diameter. As the trunk grows wider, the circumference increases, and the bark must accommodate this expansion. Different trees solve this problem in different ways, and these solutions create the distinctive bark patterns we observe. Some trees, like birch, produce bark that peels away in papery layers, constantly shedding the outer bark as it is stretched beyond its capacity to remain intact. The peeling is not damage but design, a strategy that keeps the functional layers beneath from being torn or cracked. The white color of birch bark comes from betulin, a compound that reflects light and may help protect the tree from overheating and sunscald. Other trees, like oak and pine, develop thick, deeply furrowed bark. As the trunk expands, the outer bark splits along its weakest points, creating vertical ridges and furrows. The furrows extend down through the dead outer bark, but stop before reaching the living inner bark, so the tree remains protected even as its armor cracks and separates. This thick, furrowed bark provides excellent insulation, protecting the cambium from temperature extremes and from fire. Some pines have bark so thick that they can survive ground fires that would kill trees with thinner bark, a crucial adaptation in fire-prone ecosystems. Still other trees produce bark that breaks into smaller plates or scales, creating a mosaic pattern. Sycamore bark flakes away in irregular patches, revealing lighter-colored new bark beneath and creating a mottled, camouflage-like appearance. Mature sugar pines develop bark that separates into large, flat plates with defined edges, like pieces of a three-dimensional puzzle fitted together on the trunk's surface. The texture of bark serves multiple functions beyond simply accommodating growth. The roughness provides grip for climbing animals, squirrels, insects, birds, allowing them to scale the trunk in search of food or nesting sites. The crevices and cracks create microhabitats, tiny protected spaces where insects can shelter, where spiders can anchor their webs, where moss and lichen can gain a foothold and begin to grow. Look closely at the bark of an old tree, and you will likely see these other life forms already established. Moss grows in the crevices, especially on the north side, where moisture lingers longest and sunlight is less intense. The moss is green and soft, a miniature forest growing on the forest's skin, creating its own tiny ecosystem. Beneath the moss cushions, if you were to carefully peel them back, you would find a whole community: springtails and mites, beetles and spiders, organisms so small they live their entire lives in a space smaller than your palm. Lichen clings to bark as well, those strange composite organisms that are neither plant nor fungus, but a partnership of both. Lichen grows slowly, sometimes taking years to expand by just an inch, but it is remarkably resilient, able to survive temperatures and conditions that would kill most other organisms. The lichen gives the bark a painted appearance, patches of grey, green, yellow, orange or black, depending on the species. They do not harm the tree, they merely use the bark as a substrate, gathering nutrients from rain and air rather than from the tree itself. The colour of bark varies not only between species, but also with age and environmental conditions. Young bark is often lighter, smoother, more uniform. As the tree ages and the outer bark thickens and weathers, the colour typically darkens. Exposure to sun, wind and rain creates differential weathering patterns. The south-facing side of a trunk in the northern hemisphere often develops thicker, darker, more deeply furrowed bark than the north-facing side, a response to increased sun exposure and temperature fluctuations. Some barks contain compounds that give them distinctive colours or properties. The reddish bark of madrone and manzanita is smooth and cool to the touch, almost satiny, and it peels away to reveal even brighter red-orange wood beneath. The cinnamon-coloured bark of ponderosa pine smells sweetly of vanilla when warmed by the sun, a scent created by aromatic compounds in the bark that may help deter certain insects. The black bark of charred trees after a fire often conceals living tissue beneath, the tree having survived what looked like certain death, protected by its insulating armor. Bark is also a historical record, bearing scars and signs of past events. You can read a tree's history in its bark if you know what to look for. Old wound scars where branches were lost appear as rough, thickened areas where the bark grew back over the injury. Sometimes these scars never fully heal, leaving permanent marks. Claw marks from bears or other animals that climb the trunk remain visible for decades, the bark having grown around but not erased them. The bark may show evidence of past fires, blackened areas, especially near the base of the trunk where ground fires burned. In fire-adapted species, this charring is not catastrophic, but part of the tree's expected life experience. The bark remembers the fire, bears its mark, but the tree survived and continues growing. Each fire leaves its signature, and a trunk may show evidence of multiple fires over the course of a long life. Each one survived, each one now just part of the story. Insect damage also marks the bark. Bark beetles create characteristic patterns, tiny holes where they entered, squiggly lines where their larvae tunneled between the bark and wood, sometimes elaborate galleries that look almost like abstract art. Woodpeckers excavating these insects leave larger holes, sometimes just small indentations, sometimes extensive excavations that expose the wood beneath. The tree responds by producing sap to seal the wound, creating resinous deposits that harden and protect the exposed tissue. Some trees produce special features in their bark. Cherries, birches develop horizontal lines of lenticels, tiny openings that allow gas exchange between the atmosphere and the living tissues beneath. These lenticels appear as raised dots or dashes, sometimes conspicuous enough to feel with your fingertips. They remain functional even as the bark thickens and ages, continuously forming new openings as old ones are stretched and broken by the trunk's expansion. Cork oak has perhaps the most remarkable bark of all, thick, spongy, and able to be harvested without killing the tree. Every 9 to 12 years, the outer bark can be carefully stripped away, and the tree will regenerate a new layer. This cork is composed of dead cells filled with air, making it both light and an excellent insulator. The ability to harvest bark sustainably has made cork oak economically valuable, while also ensuring the preservation of cork forests, a rare example of human use aligning with conservation. The thickness of bark is an adaptation to the tree's environment. Trees in fire-prone areas tend to develop much thicker bark than trees in wetter climates where fire is rare. Giant sequoias, which can live in areas that burn regularly, develop bark that can be more than a foot thick near the base of the trunk, insulating the cambium so effectively that the tree can survive fires hot enough to kill nearly everything else. The thick bark is spongy, filled with tannic acid that resists burning, and contains very little resin that might fuel the flames. In contrast, trees in tropical rainforests, where fire is virtually unknown, often have very thin, smooth bark. Without the threat of fire, there is no selective pressure to develop thick protective layers, and the tree invests its resources elsewhere. Some tropical trees have such thin bark that the green photosynthetic tissues beneath are visible through it, allowing the trunk itself to contribute to the tree's energy production. Run your hand over the bark once more, slowly, attending to every detail your fingertips encounter. Feel the temperature of it, slightly cooler than the air, a testament to the moisture it contains and the shade it provides to its own surface. Feel the texture, rough or smooth, deeply furrowed or gently undulating, peeling or firmly attached. Press gently and feel the slight give of the outer layers, the solid resistance of the wood beneath. This bark is not merely covering, it is interface. It is where the tree meets the world, where internal and external negotiate their relationship. It breathes through its lenticels. It weeps sap from wounds. It harbors whole communities of other organisms. It records time and trauma and survival. It is both armor and canvas, both protection and proclamation. The bark will outlast you. It was here before you arrived in this forest, and it will be here after you leave. It is adding microscopic layers even now, growing imperceptibly but continuously, accommodating the tree's endless expansion, maintaining its integrity, while allowing for change. It is patient in a way that human skin cannot be, durable in a way that human buildings are not, and it performs its multiple functions simultaneously and without rest. Look around at the many trees surrounding you and observe the diversity of bark textures and patterns. No two are exactly alike, even within the same species. Each tree has developed its bark in response to its particular circumstances, its particular history of growth and injury and survival. Each bark is unique, a signature, an individual expression of a common genetic blueprint modified by experience and environment. This is the architecture of bark, layered, functional, beautiful in its variety, essential in its purpose. It is the skin of the forest, the boundary and connection between tree and world, between inside and outside, between the hidden life within and the visible presence without. And it is here, all around you, waiting to be touched, to be read, to tell its stories to anyone patient enough to listen. Look upward now, through the lattice of branches, toward the canopy where the leaves wait in their thousands, in their millions. They appear still from here, these leaves, hanging in the filtered light like green prayers. But they are not still. They are breathing. They are working. They are performing the quiet alchemy that transforms light into life, that takes the insubstantial air and the energy of the sun and creates from these the solid substance of the tree itself. Each leaf is a small miracle of engineering, a solar panel more sophisticated than anything human technology has yet achieved, so thin that light passes through it, revealing the delicate network of veins within, yet strong enough to last an entire season, to withstand wind and rain, to repair minor damage and continue functioning. The leaf is both factory and laboratory, both lung and stomach, breathing in and breathing out in cycles that connect the tree to the atmosphere in ways both ancient and essential. Begin with a single leaf. Choose one in your mind's eye, perhaps an oak leaf with its characteristic lobed shape, or a maple leaf with its pointed tips, or the simple oval of a beech leaf, smooth-edged and symmetrical. Hold this image and let us explore it together, moving from the surface inward, discovering the hidden complexity that makes life possible. The surface of the leaf is not as smooth as it appears from a distance. If you could shrink yourself down to the size of a water droplet and walk across the leaf surface, you would find yourself in a landscape of subtle textures and remarkable features. The outer surface, the cuticle, is coated with a waxy layer that repels water, preventing the leaf from becoming waterlogged in rain and reducing water loss in dry conditions. This waxy coating gives many leaves their slight shine, their ability to bead water rather than absorb it. Embedded in this surface, invisible to the naked eye, but numbering in the thousands on every leaf, are the stomata, tiny pores that can open and close, controlling the exchange of gases between the leaf's interior and the outside air. Each stoma, in its singular form, is guarded by two specialized cells that change shape in response to light and water availability, swelling to open the pore or shrinking to close it. These guard cells are the gatekeepers, the regulators, constantly adjusting to balance the leaf's competing needs. When a stoma opens, carbon dioxide from the air can enter the leaf, passing through the pore and into the spaces between the cells within. This carbon dioxide is essential. It is one of the raw materials of photosynthesis, the source of the carbon atoms that will be assembled into sugars and eventually into all the organic molecules the tree needs. But when the stomata open to admit carbon dioxide, water vapor can escape, evaporating from the moist cell surfaces inside the leaf and diffusing out into the drier air beyond. This is transpiration, the constant loss of water that creates the pull, drawing more water upward through the tree, as we explored in an earlier chapter. The leaf must balance these two imperatives, gathering carbon dioxide while conserving water. Open the stomata too wide or for too long, and the leaf loses water faster than the roots can replace it, risking dehydration and death. Close the stomata too tightly or for too long, and photosynthesis slows or stops, starving the tree of energy. The guard cells perform this balancing act continuously, responding to light levels, humidity, internal water status, and even the time of day, opening wider in bright light when photosynthesis can proceed rapidly, closing partially or completely in darkness or in drought conditions. Beneath the surface, inside the leaf, lies a world of extraordinary organization. The leaf is composed of layers of cells, each type specialized for particular functions. Just below the upper surface lies the palisade layer, cells that stand upright like soldiers in formation, packed with chloroplasts, the tiny green organelles where photosynthesis occurs. These palisade cells are positioned to capture the maximum amount of light entering through the upper surface of the leaf. Each cell might contain dozens of chloroplasts, and each chloroplast contains the green pigment chlorophyll, the molecule that gives leaves their color and makes photosynthesis possible. Below the palisade layer lies the spongy mesophyll, cells arranged more loosely with air spaces between them. These air spaces are crucial. They allow carbon dioxide to diffuse throughout the leaf's interior, reaching all the photosynthesizing cells, and they provide pathways for water vapor to move toward the stomata. The spongy mesophyll is aptly named. It has a porous, airy structure that maximizes surface area for gas exchange while maintaining enough cellular structure to keep the leaf intact and functional. Running through these layers, creating a visible pattern when you hold a leaf up to the light, are the veins, the leaf's supply lines and structural supports. The veins contain xylem and phloem, miniature versions of the vascular systems that run through the trunk. Water arrives through the xylem, delivered to every part of the leaf, while the sugars produced by photosynthesis are loaded into the phloem and transported away to feed the rest of the tree. The pattern of veins differs among species, parallel in grasses and monocots, branching and net-like in most trees. But the function remains the same: distribution and support. Now let us descend deeper into the molecular magic that happens inside those chloroplasts. Photosynthesis is perhaps the most important chemical process on Earth, the foundation of nearly all life, the mechanism by which the energy of the sun is captured and made available to living things. It is complex in its details, involving dozens of different molecules and multiple steps, but its essential nature is beautiful in its simplicity. Light strikes the chlorophyll molecule. The energy of that light excites electrons within the chlorophyll, raising them to higher energy states. These energized electrons are passed through a chain of carrier molecules, and as they move, their energy is used to pump protons across membranes, creating a concentration gradient. When the protons flow back down this gradient, their movement drives the synthesis of ATP, the energy currency of all cells. Meanwhile, the electron's energy is also used to split water molecules, breaking apart H2O into hydrogen and oxygen. The oxygen is released as a waste product into the leaf's interior, then out through the stomata into the air, where it becomes part of the oxygen we breathe. The hydrogen from the split water molecules, along with the energy stored in ATP, is then used to power a separate set of reactions called the Calvin cycle. Here, in a marvel of molecular organization, carbon dioxide molecules are captured and combined with other molecules in a series of steps that eventually produce glucose, a simple sugar. The glucose can be used immediately for energy, can be combined into larger molecules for storage, or can be transported to other parts of the tree to fuel growth and metabolism. This process, light energy captured, water split, carbon dioxide fixed into organic molecules, oxygen released, happens in every chloroplast, in every palisade cell, in every leaf, billions upon billions of times per second. The scale is staggering. A single mature tree might have hundreds of thousands of leaves, each leaf containing millions of cells, each cell containing dozens of chloroplasts, each chloroplast conducting thousands of photosynthetic reactions per second. The cumulative effect is the creation of tons of organic matter over the course of a growing season, all built from nothing more substantial than air, water, and light. The oxygen released by the leaves, breath of the forest. In a very real sense, when you breathe in this forest, you're breathing what the trees have breathed out. The air you draw into your lungs carries oxygen molecules that moments ago were part of water molecules in a leaf, that were split apart by the energy of sunlight and released through stomata into the spaces between the trees. The trees breathe out, and we breathe in. We breathe out carbon dioxide, and the trees take it in through their stomata, using it to build themselves. It is a partnership as old as life on land, a mutual exchange that sustains both tree and animal, plant and human. The leaves know the sun's arc across the sky. Many leaves can orient themselves to track the light, adjusting their angle throughout the day to maximize exposure when light is abundant, or to minimize it when the leaf is in danger of overheating or losing too much water. This movement is subtle, usually too slow to observe directly, but time-lapse photography reveals it clearly. Leaves turning to follow the sun like small green satellites tracking their source of power. In some trees, the leaves arrange themselves in patterns that minimize shading of lower leaves by upper ones. This is called leaf mosaicing, and it creates those beautiful patterns you sometimes see when looking up through a canopy, where the leaves fit together like puzzle pieces, overlapping minimally, allowing light to reach as many leaves as possible. The tree as a whole acts as if it is solving an optimization problem, arranging its solar collectors to capture the maximum energy from the available light. The color of leaves speaks to the pigments they contain. Chlorophyll dominates in healthy, actively photosynthesizing leaves, giving them their characteristic green. But other pigments are present as well, carotenoids that appear yellow and orange, anthocyanins that can create red and purple hues. During the growing season, these other pigments are masked by the abundance of chlorophyll, but they are there nonetheless, serving as accessory pigments that capture wavelengths of light that chlorophyll cannot, extending the range of useful light energy the leaf can harvest. As seasons change, as days shorten and temperatures cool in temperate forests, the trees begin to prepare for winter dormancy. Photosynthesis slows and eventually stops. The tree withdraws nutrients from its leaves, breaking down proteins and chlorophyll and transporting the valuable components back into the branches and trunk for storage. As the chlorophyll disappears, the other pigments that were always present become visible. The leaves transform into the brilliant colors of autumn, yellows from carotenoids, reds and purples from anthocyanins, browns from the tannins that remain after everything else has been scavenged. This display, so beautiful to human eyes, is actually a practical process of resource recovery, the tree salvaging what it can before discarding the leaves entirely. But we are not yet in autumn. Here, in this moment, the leaves are green and full of life, breathing and photosynthesizing, converting light into the substance of the tree itself. They are the tree's primary interface with the sun, the collectors of the energy that powers everything else the tree does. Without leaves, there would be no growth, no flowers, no fruit, no seeds. Without leaves, the roots could not grow, the trunk could not thicken, the tree could not survive. Feel the presence of the leaves above you. Even if you cannot see each individual one, they form a ceiling, a green cathedral roof that filters the light into the gentle illumination that reaches you here on the forest floor. Each leaf is doing its work, quietly, ceaselessly, breathing in carbon dioxide and breathing out oxygen, pulling water upward from the roots, creating sugars that flow downward to feed the tree's growth. The leaves are also habitat. On their surfaces, invisible to your unaided eye, live communities of microorganisms, bacteria and fungi, yeasts and archaea. The phylosphere, it is called, the microbial ecosystem of the leaf surface. Some of these microbes protect the leaf from pathogens, competing with harmful organisms for space and resources. Others may help the leaf obtain nutrients. Still others are simply there, living out their microscopic lives on this green surface, part of the endless complexity of life in all its scales and forms. Larger creatures interact with leaves as well. Caterpillars and beetles feed on them, chewing irregular holes or consuming entire leaves. The tree tolerates some of this damage. A certain amount of herbivory is inevitable, but it is not defenseless. Many leaves produce compounds that make them less palatable or even toxic to would-be feeders. When one leaf is damaged, chemical signals can spread to neighboring leaves, triggering them to increase their production of defensive compounds. The tree communicates danger internally, mobilizes its defenses, fights back with chemistry rather than motion. The breathing of leaves is constant during the growing season, pausing only at night when photosynthesis stops without light. But even at night, the leaves continue cellular respiration, using some of the sugars they created during the day to power their own cellular processes, consuming oxygen and releasing carbon dioxide in a reversal of photosynthesis. The balance, though, is strongly in favor of net oxygen production. Over the course of a day, a tree produces far more oxygen than it consumes, releases far more than it needs, gives to the atmosphere more than it takes. Stand beneath the canopy, in the green-tinged light, and breathe deeply. The air here feels different, cleaner somehow, richer. Perhaps it is psychological, the knowledge of where you are affecting your perception. But perhaps, too, it is real. The air carrying more oxygen, carrying the fresh exhalations of thousands of leaves, performing their ancient alchemy, creating the very atmosphere that makes your life possible. The leaves above you are breathing. They have been breathing all morning, all yesterday, all through the countless days of this growing season. They will breathe tomorrow and the day after, until the changing seasons signal them to stop, to transform, to let go. But that is months away. For now, for this present moment, they breathe. And in breathing, they sustain not only themselves, not only their tree, but the forest entire and the creatures within it. And ultimately, improbably, miraculously, you. This is the breathing of leaves. Quiet, essential, generous beyond measure. The foundation of all that lives and grows in the light. If you could slice through the trunk of one of these trees, and we will not, for we honor the living. If you could see inside to where the wood reveals its secrets, you would find circles within circles, rings within rings, each one a year, each one a story, each one a record of time made visible in the pattern of the grain. These are the growth rings, the annual increments, the tree's autobiography written in wood. They are the visible manifestation of the cambium's work, that thin layer of dividing cells we have mentioned before, adding new xylem to the inside year after year, slowly building the radius of the trunk, slowly transforming slender sapling into towering elder. Each ring represents one complete cycle of the seasons, one journey around the sun. In temperate climates where seasons are distinct, the pattern is clear and regular. In spring, when water is abundant and growth vigorous, the cambium produces xylem cells that are large and thin-walled, optimized for transporting the massive quantities of water needed for the flush of new leaves and rapid growth. This spring wood is lighter in color, more porous, softer. As summer progresses and then yields to autumn, growth slows. The cells produced become smaller, their walls thicker, creating denser, darker wood, the summer wood or late wood. The transition from the dense late wood of one year to the light spring wood of the next creates the visible boundary, the ring, marking where one year ended and another began. To count the rings is to count the years. A tree 50 rings wide has lived 50 years. A tree with 200 rings has stood for 2 centuries, has witnessed the passage of generations of human lives, has felt the sun rise and set more than 70,000 times. Some trees, in special places, bear thousands of rings, bristlecone pines clinging to mountain slopes, trees that were already ancient when Rome was young, that carry within them records of climate and atmosphere from ages lost to human memory. But the rings tell more than just age. They tell of good years and poor years, of abundance and stress, of drought and plenty. A wide ring indicates a year of favorable conditions, ample rain, warm temperatures, good growing weather. The tree grew vigorously, adding substantial girth to its growth trunk. A narrow ring, sometimes barely visible without magnification, speaks of hardship, drought perhaps, or unusually cold temperatures, or defoliation by insects that stripped away the leaves and halted photosynthesis. The tree survived, but barely grew, investing its limited resources in maintaining existing tissue rather than creating new bulk. In this way, the rings become a chronicle not just of the tree, but of the environment it lived in. Scientists who study tree rings, dendrochronologists they are called, can read climate history in the wood. They can identify years of drought centuries past, can track changes in temperature and precipitation, can even detect major events like volcanic eruptions that cooled the climate globally and left their signature in narrowed rings across continents. The trees remember what human records have forgotten or never knew. The growth rings form in a pattern of perfect geometry. Each new ring encircles all the rings before it, adding a uniform layer around the entire circumference of the trunk. The cambium is a continuous sheath of dividing cells, not just on the trunk, but extending up into every branch and down into the major roots. Wherever there is cambium, there is the potential for growth, for the addition of new rings, for the expansion of the tree's woody structure. But the growth is not always perfectly uniform. If a tree leans or is pushed by prevailing winds, it compensates by growing more wood on the side that must support the extra stress. This creates eccentric rings, wider on one side than the other, the tree reinforcing itself where reinforcement is needed most. The same principle applies if a tree loses a major branch or if part of its crown is damaged. The cambium adjusts its growth to maintain structural integrity, growing more vigorously where more support is required, creating visible asymmetries in the ring pattern that document the tree's history of injury and adaptation. The wood itself changes character as the tree ages. The newest rings, just inside the cambium, are the sapwood, lighter in color, still actively involved in water transport, still living, in the sense that their vessels are open and functional. But deeper inside, toward the center of the trunk, the older rings have transformed into heartwood. In this inner core, The xylem vessels have been sealed off, filled with resins, tannins, and other compounds that make the wood more resistant to decay. The heartwood no longer transports water, but it provides crucial structural support. It is denser, harder, often darker in color, and more durable than sapwood. This transformation from sapwood to heartwood happens gradually, ring by ring, as the tree grows outward and the inner wood is no longer needed for active transport. The exact age at which sapwood becomes heartwood varies by species and by individual tree, but the process is inevitable. A very old tree might have only a thin shell of sapwood surrounding a massive core of heartwood, the accumulated centuries of growth preserved in the dark, dense center. The distinction between sapwood and heartwood is often visible even from outside the tree, particularly if the trunk is wounded and the interior is exposed. The heartwood's darker color, deep red in redwood, rich brown in walnut, black in ebony, speaks to the compounds it contains, the chemical defenses that prevent fungi and bacteria from decomposing it. These heartwood compounds are why certain woods are prized for durability, why they can be used in construction and remain sound for decades or centuries. Within each ring, there is even finer structure, invisible without magnification. The individual cells, tracheids in conifers, vessel elements and fibers in hardwoods, are arranged in precise patterns. The cell walls are composed primarily of cellulose, the same molecule that makes cotton soft and paper rigid, organized into fibers that give wood its strength. Lignin, that other crucial component, fills the spaces between the cellulose fibers, providing rigidity and resistance to compression. The combination of cellulose and lignin creates a composite material of remarkable properties: strong in tension and compression, relatively light for its strength, flexible enough to bend without breaking in moderate winds, yet rigid enough to support tremendous weight. The process of ring formation is one of exquisite timing and coordination. In spring, as temperatures warm and day length increases, hormones signal the cambium to resume active division. Cells multiply, differentiate, expand. The new xylem cells grow to their full size, while their walls are still thin and flexible. Then begin the process of wall thickening and lignification that will give them their final form. In most cells, the end walls dissolve away, turning isolated cells into continuous tubes for water transport. Finally, the cells die, leaving behind their carefully constructed walls, hollow tubes through which water can flow, fibers that provide strength, all organized into the annual increment that is that year's growth ring. As summer fades toward autumn, hormonal signals change. Growth slows. The cells produced are smaller, their walls proportionally thicker. By the time cold weather arrives, or dry season in climates where that is the limiting factor, growth ceases entirely. The cambium becomes dormant, its cells resting through the winter, waiting for the signals of spring to activate them once more. This dormancy is essential in climates with freezing winters. Active growth during cold weather would be fatal to the delicate dividing cells of the cambium. In tropical regions where there is no pronounced dry season or cold winter, the pattern is less clear. Some tropical trees produce growth rings in response to subtle seasonal variations in rainfall or temperature. Others grow more or less continuously and show no distinct rings at all. For these trees, aging becomes more difficult, requiring other methods, carbon dating for instance, or architectural analysis of branching patterns. The rings also record events beyond just climate. Fire scars appear as darkened areas where flames burn through the bark into the wood. The tree, if it survived, sealed off the damaged area and continued growing, but the scar remains visible in cross-section, marking the year of the fire. Successive fire scars can show a pattern of periodic burning, documenting the natural fire regime of the forest. In the American West, many old ponderosa pines show fire scars from ground fires that burned through every few decades before modern fire suppression. Fires that were not catastrophic, but cleansing, removing understory fuel and maintaining open, park-like forests. Insect outbreaks leave their signature too. A year when defoliating insects stripped a tree of its leaves would show as a narrowed ring, the tree having produced little growth without its photosynthetic capacity. If the outbreak lasted several years, there would be a sequence of narrow rings. Recovery appears as rings widening again, returning to normal as the insect population crashed and the tree refoliated. Even individual growth rings contain variation that tells of conditions within that particular growing season. In some species, individual cells within a ring can show stress bands, dark lines that mark periods when growth paused due to drought or other stress, then resumed when conditions improved. A single ring might contain several such bands if the growing season was interrupted multiple times, each pause and resumption recorded in the pattern of cell wall thickness. The geometry of growth rings has implications for the tree's mechanical properties. Wood is not uniform in strength. It is stronger along the grain than across it, because the long cells and fibers are oriented vertically. This makes wood easy to split along its length, but difficult to break across. The rings themselves create planes of potential weakness, as the transition from dense latewood to porous springwood is a boundary where splitting can occur more easily. Yet for all these directional differences, wood remains one of nature's most successful structural materials, combining adequate strength with light weight and ready availability. The patience required to build these rings year after year is beyond human comprehension. We live fast, accomplish in years what we set out to do, measure success in terms visible within our lifetimes. But a tree operates on a different timescale. Each ring is a sliver of thickness, often less than a quarter inch, sometimes less than a tenth of an inch. To add 12 inches to its radius, to double its diameter, a tree must lay down dozens of rings, must live through dozens of complete seasonal cycles, must stand patiently in one spot while decades pass. And yet, this is not experienced by the tree as waiting. The tree does not long for the future or regret the past. It exists completely in the present, responding to current conditions, growing when conditions permit, dormant when they do not. Each moment is full. Each ring is the tree's entire focus as it forms. And when it is complete, the tree moves on to the next, with no attachment to what has been built, no anxiety about what is to come. There is wisdom in this patience, in this steady accumulation of incremental growth. The tree does not strive to grow faster than conditions permit. It does not compare itself to neighboring trees and feel inadequate if they have wider rings. It simply grows at the rate that its particular circumstances allow, and over time, this patient accumulation results in size and strength and longevity that no amount of rushed growth could achieve. The rings are forming right now, at this very moment, in every tree around you. The cambium is active, cells are dividing, new wood is being added, layer by infinitesimal layer. You cannot see it happening. It is far too slow for that. But it is as real as your own breathing, as certain as the turning of the earth. By this time next year, each tree will have added one more ring, will have expanded its girth by one more increment, will have built one more year's worth of structure to support its reaching toward the light. Imagine yourself standing here 1 year from now, in the same spot, among the same trees. They will look almost identical to how they appear today. The difference will be imperceptible to casual observation, but the difference will be real nonetheless. One more ring in every trunk, one more layer added to centuries or decades of accumulated growth, one more year's story written in wood and waiting to be read by anyone who knows the language of rings. This is the patience of growth rings, slow, steady, cumulative, honest. They cannot be rushed, cannot be faked, cannot be anything other than what they are. The truth of each tree's experience, written in circles, preserved in wood, patient beyond measure. Look up again, past the textured columns of the trunks, up into the network of branches that divide and subdivide, reaching outward and upward in patterns that seem both random and purposeful, chaotic and ordered. This is the society of branches, the tree's architecture of air and light, each branch a member of a community that works together to support the crown, to hold the leaves aloft, to present the maximum surface area to the sun, while maintaining the structural integrity of the whole. A branch begins as something impossibly small, a bud, a tiny cluster of cells protected by overlapping scales, waiting through winter or dry season for the signal to grow. When conditions are right, when warmth and moisture return, the bud swells. The scales that protected it through dormancy loosen and fall away, and from within emerges a shoot, tender and pale green, elongating with astonishing speed compared to the slow radial growth of the trunk. This is primary growth, the extension of the tree upward and outward, the creation of new length rather than new girth. The young shoot grows from its tip, from the apical meristem, a dome of actively dividing cells at the very end. Behind this growing tip, the stem elongates, cells stretching to their full length, pushing the tip steadily forward. Leaves unfurl along the lengthening stem, each one emerging from its own protective bud, expanding from a tightly folded package into the flat, light-capturing surface we explored in an earlier chapter. The shoot grows rapidly during its first season, several inches, sometimes several feet, depending on species and conditions, then hardens off as the season progresses, its tender green skin thickening into bark, its interior tissues developing the vascular connections that will integrate it into the tree's transport system. In subsequent years, this branch that began as a single season's shoot will grow longer from its tip and thicker from its cambium. It will produce side branches of its own, smaller shoots that emerge from buds along its length, creating the next order of division in the tree's branching hierarchy. These secondary branches will in turn produce tertiary branches, and those may produce even finer divisions, until, at the outermost edge of the crown, the finest twigs bear the leaves, the ultimate purpose of all this structural elaboration. The pattern of branching varies by species, but it follows rules, patterns encoded in the tree's genetics and modified by the particular conditions each tree experiences. Some trees, like pines and firs, show a strongly whorled pattern, with branches emerging in regular circles around the trunk, at intervals that mark each year's growth. Count the whorls and you count the years, at least in young trees, before the lower branches are lost and the pattern becomes less distinct. Other trees branch more irregularly. Oaks and maples produce branches alternately or in pairs along the trunk and along each branch, creating a more complex, less geometrically obvious pattern. Yet, even in this apparent irregularity, there is order. The angle at which a branch diverges from the trunk is characteristic of the species, narrow and acute in some, wide and nearly perpendicular in others. This branch angle affects the tree's overall shape, helping create the spreading crown of an oak, the conical form of a spruce, the vase shape of an elm. The branches do not grow independently, they communicate and coordinate. Hormones produced by the terminal bud at the tip of each branch suppress the growth of lateral buds along that branch's length, a phenomenon called apical dominance. This ensures that the branch grows primarily from its tip, rather than producing excessive side branches that would make the structure bushy and weak. But if the terminal bud is damaged or removed, by browsing animals, by storm, by pruning, the suppression lifts, and the lateral buds are released to grow. often producing several new shoots in place of the lost leader. The tree as a whole also coordinates its branches through hormone signals. The main trunk typically shows stronger apical dominance than side branches, maintaining its position as the primary axis of the tree. But in some species, especially as trees mature, this dominance weakens, and the tree develops a more rounded, spreading crown where no single leader dominates. The shape you see in the crown is the result of countless small decisions made by buds responding to hormonal signals, to light availability, to mechanical stress, creating a form that is both genetically determined and environmentally shaped. Branches must be strong. They bear not only their own weight, but the weight of all the branches that arise from them, all the leaves they carry, the accumulated rain or snow that may load them, the forces of wind that push against their surface area. The wood of branches must resist bending and breaking, must flex under stress but return to its original position, must be engineered to avoid catastrophic failure. Where a branch joins the trunk or joins another branch, the union is not simply a weak point of attachment, but a carefully engineered joint. The branch collar, that slightly swollen area at the base of a branch, contains wood fibers arranged in interlocking patterns that provide exceptional strength. The grain of the wood in the trunk flows around the branch, integrating it into the structure. The result is a joint that is often stronger than the branch or trunk itself, able to withstand forces that would break either individual member. Still, branches do fail. Under extreme loads, ice storms, heavy wet snow, violent winds, even strong branches can break. Usually the break occurs not at the joint, but partway along the branch's length, at a point where decay has weakened the wood or where the leverage of the load exceeds the wood's breaking strength. The tree responds to such losses by sealing the wound, producing callus tissue that eventually covers the broken stub, and by releasing suppressed buds elsewhere in the crown to grow and fill the gap in the canopy. The spacing of branches on the trunk is not arbitrary. Branches emerge along a spiral pattern around the trunk's circumference, each one at a slightly different angle than the one before it. If you trace this spiral, you find that it follows mathematical ratios, the Fibonacci sequence, the golden angle, the same patterns that appear in pine cones and sunflower heads and nautilus shells. This arrangement ensures that branches are distributed around the trunk in a way that minimizes shading of lower branches by upper ones and maximizes the structural stability of the crown. Light governs much of branch behavior. Branches grow toward light, bending slowly over time to position themselves in sunny gaps in the canopy. This phototropic response allows trees to adjust their crown architecture to the light environment. In a dense forest, where competition for light is intense, branches tend to be sparse and concentrated high in the crown, where they can reach above competitors. In open-grown trees, where light is abundant from all directions, branches spread widely at multiple levels, creating the full, rounded crowns characteristic of isolated specimen trees. The lower branches of forest trees often die and fall away as the tree grows taller and the crown rises. Shaded by the upper canopy, these lower branches no longer receive enough light to photosynthesize more than they respire. They become net consumers of resources rather than producers, and the tree withdraws nutrients from them and allows them to die. Eventually, the dead branches break off or decay, and the trunk grows over the stub, leaving only a knot in the wood to mark where the branch once lived. This self-pruning is efficient, allowing the tree to maintain only the branches that contribute to its energy budget. Yet not all lower branches are sacrificed. Some trees retain living branches close to the ground throughout their lives, especially in species adapted to open environments. The strategy depends on the species' ecology, on whether it evolved in dense forests, where height is crucial, or in more open settings, where a full crown from ground to tip captures maximum light. Branches also serve as habitat. Their structure creates niches and opportunities for other organisms. Birds nest in the forks between branches, choosing locations that provide both support and concealment. Squirrels run along branches as highways through the canopy, leaping between trees without descending to the ground. Insects mine beneath bark, bore into wood, create galls and shelters. Lichens and mosses colonize the upper surfaces of horizontal branches, finding there a stable substrate and access to light filtered through the leaves above. In tropical forests, branches may support entire gardens of epiphytes, orchids, bromeliads, ferns, plants that grow on the branches without parasitizing the tree, using it merely as a platform to reach the light. These epiphyte communities can be so dense that the branches accumulate soil and organic matter, creating hanging gardens that harbor their own invertebrate communities, their own frogs and lizards, entire ecosystems suspended in air. The oldest branches, the lowest ones that persist on ancient trees, may be centuries old themselves. In some species, the largest horizontal branches of very old trees have diameters rivaling the trunks of younger trees. These ancient limbs have their own growth rings, their own history recorded in wood. They have flexed under countless windstorms, have borne the weight of countless snows, have supported generations of leaves that rose each spring and fell each autumn in cycles too numerous to count. The society of branches is cooperative, but also competitive in a gentle way. Each branch reaches toward available light, filling space that would otherwise be captured by a neighbor. Yet the competition is constrained by the fact that all branches are part of the same organism. The tree does not benefit if one branch outcompetes another to the point of killing it. Rather, the tree benefits from an even distribution of branches that maximizes total light capture while maintaining structural stability. There is beauty in this branching pattern, a fractal beauty where the pattern of the whole is repeated at smaller and smaller scales. The way the trunk divides into major limbs resembles the way each major limb divides into smaller branches, which resembles the way each small branch divides into twigs. The same angles, the same relationships, repeated across orders of magnitude, creating a self-similar structure that is both mathematically elegant and aesthetically pleasing. Artists and photographers know this beauty. The silhouette of a bare winter tree, branches stark against sky, reveals the architecture that is hidden during the leafy season. The form is intricate, each tree unique in its exact configuration, yet characteristic of its species in its overall pattern. The spreading oak, the ascending maple, the weeping willow, each has its signature shape, its characteristic way of dividing space. In winter, when leaves have fallen and growth has ceased, the branches wait. They appear lifeless, grey or brown, stark and still. But they are not lifeless. Inside each twig, protected by bud scales, next year's leaves and shoots wait in miniature, already formed, merely waiting for the signal to unfold. The branches themselves remain alive, their cambium dormant but ready, their vascular tissues ready to resume transport when sap begins to flow in spring. The apparent death of winter is only dormancy, only waiting, only the patient interval before renewal. Watch a branch move in the wind. It bends, flexes, returns. It does not resist the wind rigidly, but yields to it, allowing the force to pass through and dissipate without causing damage. This flexibility is crucial to survival. A rigid branch would snap under the same loads that a flexible branch accommodates. The wood has just the right combination of stiffness and flexibility, engineered by evolution to survive the mechanical stresses of life in the canopy. The branches around you now, reaching upward and outward in their intricate patterns, are holding thousands of leaves in the light. They are carrying water from roots to crown, and sugars from crown to roots. They are swaying slightly in the gentle breeze, flexing and returning, alive and patient. They have grown slowly to their current size and will continue growing, adding rings and length, as long as light and life persist. This is the society of branches, structured yet organic, strong yet flexible, individual yet integrated. Each branch is distinct, yet all are connected, all part of the greater whole that is the tree. They reach, they support, they divide and share space and light, creating together the crown that defines the tree's presence in the forest, the architecture that transforms a vertical trunk into a three-dimensional exploration of the space between earth and sky. Listen now. Be very still and listen. Do you hear it? Perhaps not yet, but soon. The air is changing, becoming heavier, cooler. The light has shifted, diffused through clouds that have gathered without announcement, as they always do in the forest, moving in on silent currents high above the canopy. The rain is coming. You can feel it in the air before a single drop falls. A tension, an expectation, the forest itself seeming to pause and wait. And then, the first drop. It falls from a height you cannot see, from clouds thousands of feet above, condensing from vapor into liquid around a speck of dust or salt, growing heavier, falling, accelerating through the atmosphere until it reaches terminal velocity, falling at perhaps 20 miles per hour, falling for perhaps a minute or more before it strikes the first leaf at the top of the canopy. That impact, drop meeting leaf, creates a sound so small you would never hear it individually. But the drop is not alone. Behind it come thousands more, millions more, a numberless multitude of drops, all falling, all striking leaves and branches, creating together a sound like whispered applause, like distant static, like the softest drumming on the largest drum ever made. The rain has arrived. The first drops to reach the canopy do not immediately reach you. They strike the uppermost leaves, those that form the forest ceiling, and there they pause. Some drops splash on impact, breaking into smaller droplets that scatter in all directions. Some drops are caught in the cup of a curved leaf and sit there, trembling with the leaf's slight movements, held by surface tension until enough water accumulates to overcome the holding force and spill over the edge. Other drops slide along the leaf surface, following the veins toward the stem, coalescing with other drops, growing larger, moving downward along the branch toward the trunk. This is the interception of rain, the forest's first engagement with water falling from sky. The canopy intercepts a surprising amount. In a dense forest, perhaps 20 to 40% of rainfall never reaches the ground directly, but is captured by leaves, branches, and bark. Some of this intercepted water evaporates back into the atmosphere without ever feeding the soil. It wets the surfaces, increases local humidity, cools the air, and then disappears, recycled back into the hydrological cycle. But much does continue downward. The drops that are not immediately evaporated begin their secondary journey, no longer falling straight from cloud, but trickling, dripping, channeling through the architecture of branches and leaves. Watch how the water moves. A drop slides down a leaf surface to the pointed tip. Many leaves taper to a drip tip for precisely this reason. And there it hangs for a moment, growing as other drops join it, until gravity overcomes surface tension and it falls again, continuing its interrupted descent. Some drops coalesce into larger drops on the branches. Water seeks water, the molecules attracted to each other, and what began as separate drops merge into rivulets, into tiny streams that flow along the top of a branch, following the slight downward slope, meeting other rivulets, growing into flows that carry not just water, but dissolved nutrients leached from the leaves and bark. carrying tiny particles of dust and pollen, carrying the accumulated chemistry of the canopy downward. This water that flows down branches and trunks is called stem flow, and it can be substantial. In some trees, particularly those with smooth bark and branches that angle upward, a significant portion of rainfall is channeled down the trunk, arriving at the base in a concentrated flow rather than spread diffusely across the forest floor. This stem flow carries with it nutrients, nitrogen, phosphorus, potassium leached from leaf surfaces, organic acids from bark, enriching the soil immediately around the trunk where the tree's roots are most concentrated. The sound of rain in the forest changes as more water begins to penetrate the canopy. The initial soft whisper grows into a more complex symphony. There is the patter of drops on leaves, each leaf producing a slightly different tone depending on its size, its thickness, its tension. There is the heavier thunk of larger drops that have coalesced before falling, striking leaves with more force, more authority. There is the drip, drip, drip from countless points where water has accumulated and now falls in a steady rhythm. And underneath it all, increasingly, there is the sound of rain striking the forest floor. A softer sound than rain on pavement or roof, muffled by the thick layer of fallen leaves, absorbed by the organic duff, seeping almost immediately into the porous soil. The forest floor does not produce the harsh percussion of rain on hard surfaces. Instead, it whispers acceptance, welcoming the water, drawing it in. Feel the rain now. It is reaching you, here beneath the canopy. Not as a deluge, the canopy prevents that, but as a gentle, scattered falling. A drop strikes your cheek, cool and startling. Another lands on your hand. You look up and see drops falling between the leaves, backlit by the grey light filtering through the clouds. Each drop visible for a moment as a silver sphere in freefall before it strikes surface and disappears. The rain is cold, or at least cooler than the air, carrying with it the chill of altitude, of the upper atmosphere where it formed. As it falls and strikes surfaces in the forest, it gradually warms to the ambient temperature, but its initial coolness is a gift, especially on a warm day. The temperature drops noticeably as the rain continues. The air, which was warm and still, becomes cooler and begins to move as the falling rain creates its own small currents and eddies. The smell changes too. There is a scent that rain brings to a forest, especially after a dry spell, a smell that has been given a name, petrichor, from the Greek words for stone and the fluid that flows in the veins of gods. It is caused by oils released by plants during dry periods, accumulated in the soil, liberated when rain first strikes the ground. Mixed with this is geosmin, a compound produced by soil bacteria that gives earth its characteristic smell. Together, these create that distinctive scent of rain on dry ground, a smell that is both earthy and clean, both ancient and fresh. But this forest has not been dry. Rain comes regularly here, keeping the soil moist, the moss green, the air humid. The smell is different, more subtle, more about the intensification of existing scents than the creation of new ones. The smell of wet bark, of saturated moss, of leaves heavy with water. The smell of life in moisture, of growth enabled, of the forest refreshed. The rain continues, settling into a steady rhythm. This is not a thunderstorm with its violence and drama. Those we will not speak of here, for we are seeking only peace. This is a gentle rain, the kind that can last for hours, that soaks deeply rather than running off, that the forest truly needs and uses. This is the rain that feeds the roots, that recharges the water table, that maintains the streams and seeps and springs that are the forest's circulatory system at the landscape scale. Watch the water on bark. The bark, which was dry and light-coloured, darkens as it absorbs moisture. In trees with deeply furrowed bark, water runs down the furrows like miniature waterfalls, while the ridges between remain relatively dry, protected by their elevation and by the slight overhang that the bark's texture creates. In trees with smooth bark, water sheets across the surface, turning the trunk from grey to black, making it appear almost polished, reflective. Some bark types are more absorbent than others. Cork-like bark absorbs water readily, swelling slightly, becoming softer and more pliable. Resinous bark sheds water more effectively, the resins in the wood creating a more water-resistant surface. But all bark, to some degree, accepts water, allows it to penetrate to the living. Cambium beneath maintains moisture in the outer layers where mosses and lichens cling, and where the bark's own cells, though mostly dead, still perform their protective function. The moss responds immediately to rain. Moss, which can dry to a crispy brown in drought and enter a dormant state, revives with astonishing speed when wet. Within minutes of rain beginning, dry moss begins to swell, to green, to return to active life. By the time the rain has been falling for half an hour, the moss is lush, saturated, a deeper green than it was before, every tiny leaf plump with water, every cell expanded to its full capacity. The water that reaches the forest floor begins its final descent into the soil. The layer of fallen leaves, the litter layer, is like a sponge, absorbing water, releasing it slowly downward. A thick litter layer can hold enormous amounts of water, preventing runoff even in heavy rain, metering the water's infiltration into the mineral soil beneath. The leaves in contact with the soil are partially decomposed, soft, friable, and they compress under the weight of the water, creating intimate contact between the water and the soil beneath. The soil itself is structured to receive water. The spaces between soil particles, the pore spaces, are numerous and interconnected in healthy forest soil. Water enters these pores, pulled by gravity and by capillary action, moving downward and outward, filling the spaces, displacing the air that normally occupies them. Some water is captured by clay particles, held by electrostatic attraction on their surfaces. Some water is absorbed by organic matter, by partially decomposed leaves and wood that act like sponges. And some water continues downward, percolating through the soil profile, eventually reaching the water table, the saturated zone where all pores are filled and from which the deepest roots draw their supply. But not all water moves directly downward. The fungal networks we spoke of earlier, the mycorrhizal connections between roots and fungi, create additional pathways for water movement. The fine fungal threads, the hyphae, wick water through the soil, moving it laterally as well as vertically, distributing it more evenly than gravity alone would accomplish. And the roots themselves, both living and dead, create channels through the soil, macropores that allow rapid infiltration, preferential pathways where water can move quickly downward without having to displace soil particles. The rain is also feeding the smallest members of the forest community. Tardigrades and nematodes, dormant in the soil during dry periods, activate when water becomes available. Springtails emerge and begin their microscopic grazing on fungi and bacteria. Earthworms, which had retreated to deeper, moister soil, now return to the upper layers, where fresh organic matter is available. The entire soil community responds to rain, increasing its activity, accelerating the decomposition and nutrient cycling that the forest depends upon. In puddles and depressions, temporary pools form. These may last only hours or days, but while they exist, they are habitats. Mosquito larvae may appear, hatched from eggs that waited dry for weeks or months for just such an opportunity. Salamanders may visit to drink or to hunt the small invertebrates that congregate in the water. Birds may come to bathe, splashing energetically, ruffling their feathers in the clean rainwater. The rain also brings nutrients. Rainwater is not pure H2O, but contains dissolved gases from the atmosphere: nitrogen oxides, sulfur compounds, carbon dioxide, and particles of dust and organic matter. Lightning, in storms elsewhere, converts atmospheric nitrogen into soluble nitrates that rain brings to the soil. Industrial emissions, unfortunately, also contribute sulfates and other compounds, but in a remote forest, rain remains relatively clean, a gentle fertilization as well as a hydration. The pattern of rain varies even within this small area where you stand. Beneath some trees, rain falls more heavily because the canopy funnels it through gaps or channels it down branches. Beneath others, the canopy is so dense that only a fine mist penetrates. These microhabitat differences create variation in soil moisture at very small scales, creating niches that different plants exploit. Ferns may grow in the wetter spots beneath canopy gaps. Moss proliferates where branches channel extra water down the trunk. Drier microsites may support different species adapted to less moisture. The duration of rain matters as much as its intensity. This gentle rain, falling steadily for hours, will soak deeply into the soil, recharging reserves to a depth of several feet. A brief, intense shower, even if it delivers the same total volume of water, will wet only the surface layers before ending, leaving deeper soil unaffected. The forest thrives on this patient, thorough soaking, on rain that continues long enough to saturate the entire root zone, to seep into every crevice, to ensure that no root, no matter how deep, goes thirsty. Eventually, imperceptibly at first, the rain begins to lessen. The steady patter becomes intermittent. Drops fall more slowly, the spaces between them growing longer. The sound changes from continuous to sporadic, from a unified hush to individual drips. The clouds lighten, the grey becoming brighter, though the sun itself remains hidden. The rain has not stopped, but is tapering, withdrawing as gently as it arrived. Even after the last drop has fallen from the clouds, the forest continues dripping. Water accumulated in the canopy takes time to complete its descent. For an hour or more after the rain has ended, the sound of dripping continues, from leaves, from branches, from moss-covered trunks. A diminishing echo of the rain that was, a slow release of captured water back into circulation. The air after rain is different, cleaner, clearer, as if the rain has washed not just the leaves but the air itself. The humidity is high, near saturation, and the coolness remains. Mist may form, rising from the warm soil meeting the cooled air, creating a low layer of fog that drifts between the trunks like something living, like the forest's own breath made visible. You are wet now, not soaked but damp. Your clothes carry the weight of water. Your skin feels the coolness, and you are part of the rain cycle, just as the trees are, just as the soil is. The water that touched you will evaporate, will return to the atmosphere, will condense again somewhere, will fall again, endlessly cycling through the phases and places that connect all water, all weather, all life on this planet that is, more than anything, a water world. This is the falling of rain, gentle, generous, essential. It is the sky giving to the earth, the atmosphere giving to the forest, water cycling through its eternal round, enabling life, sustaining growth, connecting cloud to soil through the medium of tree and leaf and time. Lower your gaze now. Look down from the high branches, down from the rain-darkened bark, down to the forest floor where another world exists, smaller and quieter, closer to the earth. Here, covering stones and fallen logs, creeping up the bases of trunks, carpeting the spaces between roots, grows the moss. ancient, patient, impossibly soft, and utterly silent. Moss is among the oldest of land plants, having made the transition from water to land hundreds of millions of years ago, long before flowering plants, long before trees as we know them existed. It represents an early solution to the challenge of terrestrial life, a simple but effective approach that has persisted largely unchanged while more complex plants evolved around it. To observe moss is to glimpse something primordial, something that has survived since the early chapters of life's story on land. Kneel down beside a moss-covered log, or better yet, sit on the soft forest floor and bring yourself close to this miniature landscape. What appears from a distance as a uniform green carpet reveals itself on closer inspection as a complex community. Different species growing together, each with its own particular form, its own shade of green, its own strategy for life at the forest floor's surface. Touch the moss gently. Feel how soft it is, how yielding. The sensation is unlike anything else in the forest. Not firm like bark, not substantial like leaves, but cushiony, almost unreal in its softness, as if you are touching something made of condensed air rather than living tissue. Press slightly and feel how the moss compresses, then slowly rebounds when you release the pressure. It is alive, resilient, quietly occupying space that would otherwise be bare wood or stone. Moss has no roots in the traditional sense. Those tiny hair-like structures you might see extending from the base are rhizoids, simple anchoring filaments that hold the moss to its substrate but do not absorb water and nutrients the way true roots do. Moss absorbs what it needs through its entire surface. Every leaf, every stem can take in water and dissolved minerals directly from rain, from fog, from the humid air itself. This is why moss thrives in places where the air is moist, where the forest canopy creates a constant microclimate of humidity and shade. The structure of moss is beautifully simple. Each plant is small, often just an inch or two tall, composed of a stem with tiny leaves arranged around it in spirals or rows, depending on the species. These leaves are usually just one cell thick, a single layer of cells containing chloroplasts, conducting photosynthesis, capturing what little light reaches the forest floor. Being so thin, the leaves cannot withstand drying. They have no cuticle like the thick, waxy coating on tree leaves. This is why moss is restricted to moist environments. It cannot survive prolonged drought, cannot prevent water loss the way more advanced plants can. But moss has its own strategy for dealing with dry periods. When water becomes scarce, moss does not die. It enters a state of dormancy. The cells lose most of their water. The leaves curl and shrivel. The green fades to brown or grey. The moss appears dead, crispy and lifeless to the touch. But it is not dead, merely waiting. When rain returns, as we witnessed in the previous chapter, the moss revives within minutes to hours, absorbing water rapidly through its entire surface, swelling, unfurling, returning to vibrant green and active growth. This ability to survive desiccation, to shut down and restart repeatedly, is one of moss's great survival strategies. The moss around you exists in layers, in communities of overlapping individuals. What appears to be a single cushion is actually thousands of individual plants growing so closely together that they support and shelter each other. The outer surface, exposed to air and light, consists of the living tips, the growing points. Below this surface lies an increasing thickness of older growth, stems and leaves that are no longer actively growing, but still contribute structure to the colony, creating the cushiony depth you felt when you touched it. At the very bottom of the moss cushion, in contact with the substrate, the oldest parts are dead, slowly decomposing, breaking down into organic matter that enriches the thin layer of soil accumulating beneath the moss. In this way, moss creates its own habitat, building soil where little existed before, preparing surfaces for other plants that may eventually succeed it. Moss colonizes surfaces that other plants cannot easily inhabit. Bare rock, smoothed by glaciers or exposed by landslides, is inhospitable to most plants. No soil, no place for roots to anchor, no reservoir of nutrients or water. But moss can attach itself directly to rock with its rhizoids, can absorb what it needs from rain and air, can begin the slow process of creating soil from stone. Lichens often come first, secreting acids that begin to break down rock surfaces. But moss follows quickly, its decomposing tissues adding organic matter, its presence creating tiny pockets where moisture collects and mineral particles accumulate. On fallen logs, moss plays a crucial role in decomposition. The logs that lie scattered across the forest floor, nurse logs they are called, are future soil, but their transformation from solid wood to crumbly humus takes decades. Moss accelerates this process by maintaining moisture on the log's surface, by harboring the fungi and bacteria that actually digest the wood, by creating a microenvironment that supports the entire community of decomposers. A log covered in thick moss is being actively recycled, its stored carbon and nutrients being released back into the ecosystem. The silence of moss is profound. Of all the living things in the forest, moss is perhaps the quietest. It makes no sound as it grows. Its leaves do not rustle in the wind. They are too small, too flexible. It produces no flowers, so there is no pollination drama, no visits from buzzing insects. It releases its spores silently from capsules held aloft on delicate stalks, the spores drifting away on air currents without fanfare. Moss simply exists, growing imperceptibly slowly, adding microscopic increments to its height and extent, silent in life and silent in its slow return to the soil. Look closely at the moss's reproductive structures, if they are present. At certain times of year, moss produces sporophytes, thin stalks rising above the leafy growth, topped with small capsules. These capsules contain spores, thousands of them, microscopic particles of potential life. When conditions are right, the capsule opens and the spores are released. Each spore, if it lands in a suitable location, can germinate and grow into a new moss plant. But the odds are long. Most spores fail to find the narrow window of conditions they need. Still, producing thousands of spores ensures that some succeed, that the species persists. Moss also reproduces vegetatively, fragments breaking off and establishing themselves elsewhere. This is perhaps the more reliable method. A small piece of moss carrying the complete genetic information of the parent, requiring only to land in a moist, shaded spot and continue growing. In this way, moss spreads slowly across suitable substrates, colonizing logs, rocks, soil, even the bark of trees, creating those beautiful green tapestries that soften the forest's appearance. Different species of moss occupy different niches within the forest. Some prefer the deep shade of the forest interior, thriving where light levels are so low that few other plants can photosynthesize effectively. Others colonize more open areas, fallen logs in clearings where more light penetrates. Some species specialize in very wet conditions, growing in seeps and along stream banks where water is constantly available. Others are more drought-tolerant, relatively speaking, able to survive on exposed rocks where water comes only with rain. The names of mosses, in the languages of science, are melodious: dicranum, polytrichum, hypnum, sphagnum. Each genus contains many species, each species distinguished by subtle differences in leaf shape, in the pattern of cells, in the form of the capsule. To the untrained eye, all moss might look similar, but to the bryologist, the scientist who studies mosses, Each species is as distinct as oak is from maple, as recognizable as an old friend. Sphagnum moss deserves special mention. In peatlands and bogs, sphagnum creates vast accumulations, entire landscapes of moss growing layer upon layer, the living surface floating on a deep foundation of partially decomposed, older growth. Sphagnum has the remarkable ability to acidify its environment, creating conditions so low in pH that decomposition nearly stops. Dead sphagnum doesn't fully decay, but accumulates as peat, carbon storage that can persist for thousands of years. In this way, sphagnum moss has removed enormous amounts of carbon dioxide from the atmosphere over geological time, helping to regulate the planet's climate through the simple act of growing and incompletely decaying. In this forest, however, the moss is not sphagnum, but species adapted to well-drained substrates, to the surfaces of logs and rocks and soil. These mosses form cushions and mats of varying thickness, some species creating tight, compact growth, others growing in looser, more sprawling forms. The variety is subtle but real, each species occupying its particular niche, each contributing to the overall diversity of the forest floor community. Moss provides habitat at the smallest scales. Within the moss cushion, in the spaces between stems and leaves, a whole world of tiny creatures lives. Springtails, primitive wingless insects smaller than pinheads, graze on fungi and decaying organic matter. Mites, microscopic relatives of spiders, hunt even tinier prey or feed on dead plant material. Rotifers and tardigrades, animals so small they live in the water films coating moss leaves, swim through the miniature ocean of moisture, feeding on bacteria and algae. When the moss dries out, these creatures enter dormancy alongside their host, reviving when water returns. These microfauna are not merely residents, they are essential to moss health. Their feeding activity processes organic matter, releases nutrients, controls fungal growth. Their waste products fertilize the moss. The relationship is not deliberate on either side. Moss has no awareness of the creatures it harbors, but it is real nonetheless, a web of mutual benefit that exists at scales invisible to human eyes. The color of moss is not uniform, though we speak of it as green. Look closely and you will see variation. Some moss is bright green, almost lime in its intensity. Other moss is darker, approaching olive or forest green. Some species show a yellowish tint, others a bluish cast. And the same moss can change color depending on moisture, light, and age. Brighter when wet and freshly growing, duller when dry or senescent. There is something meditative about observing moss, about lowering yourself to its level and entering its scale of existence. The forest becomes a different place when you focus on these tiny plants. The towering trees recede in importance. The drama of canopy and crown becomes background. Here, at moss level, the significant events of a slow expansion of a moss cushion across a log, the germination of a spore, the revival of dried stems after rain. It is a slower world, a quieter world, but no less alive, no less important in the functioning of the forest ecosystem. Moss is often associated with the north side of trees, and there is some truth to this. In the northern hemisphere, the north side of a tree receives less direct sunlight, retains more moisture, and provides the shady, humid conditions that moss prefers. But this is not a universal rule. Moss grows where conditions suit it, and in a dense forest where light is diffuse and humidity high from all directions, moss may encircle a trunk completely, showing no preference for orientation. The ecological role of moss extends beyond its immediate presence. By capturing and holding water, moss regulates the moisture availability on the forest floor, smoothing out the feast and famine cycle of rain and drought. By slowly decomposing and releasing nutrients, it contributes to soil fertility. By providing shelter for microfauna, it supports the base of the detrital food web, the community of organisms that processes dead organic matter and makes nutrients available for uptake by plants. Moss also indicates environmental quality. Many mosses are sensitive to air pollution, particularly sulfur dioxide and nitrogen oxides. In areas with significant air pollution, moss diversity and abundance decline. A forest rich in diverse moss species is therefore a forest with relatively clean air, a forest where the atmosphere retains something of its natural chemistry. The presence of moss is a silent testimony to environmental health. Sit here a moment longer, in this silence that moss embodies. Let your eyes rest on the green cushions, on the way light catches on the tiny leaves, creating a texture of infinite subtlety. Let your mind quiet to match the moss's quietness. There is no urgency here, no rush, no loud growth or dramatic events. There is only the patient accumulation of tiny plants, the slow greening of surfaces, the quiet work of living at the smallest scales of the forest. This is the silence of moss, profound, complete, peaceful. It is the silence of things that have found their place and are content in it, that grow without ambition, that exist without needing to announce their existence. It is the silence of the forest floor, of spaces beneath notice, of life lived small and slow and persistent. And in this silence, there is a kind of wisdom, a reminder that not all important things are large or fast or loud, that patience has its own power, that softness can endure where hardness shatters. Beneath the moss, beneath the fallen leaves, beneath the visible surface where your feet rest, lies the soil, dark, rich, complex beyond measure. It is easy to think of soil as mere dirt, as inert material, as the passive stage on which life performs. But soil is not passive. Soil is alive, teeming with organisms, structured by the slow work of decay and transformation, and it is as essential to the forest as air or water or light. Take a handful of this forest soil. Feel its texture between your fingers. It is soft, crumbly, not dense or clayey, but loose and friable, easy to compress, yet holding its form. The color is dark brown, almost black, the color of organic matter, of carbon, of life transformed and transforming. Bring it close and smell it, that earthy, musty scent, neither pleasant nor unpleasant, but deeply familiar, the smell of ground itself, of the substrate from which all terrestrial life ultimately arises. This handful contains more organisms than there are humans on Earth. Billions of bacteria, millions of fungi, thousands of protozoa, hundreds of nematodes, dozens of arthropods, all in this single handful, all alive, all active, all engaged in the work of decomposition and nutrient cycling that makes the forest possible. You cannot see most of them. They are microscopic, invisible without magnification, but they are there, as real and important as the trees towering above. Soil is not merely ground-up rock, though rock is part of its composition. The mineral component, sand, silt, clay, comes from the weathering of bedrock, the slow breakdown of stone into ever smaller particles. This weathering happens through multiple mechanisms: water freezing in cracks and expanding, roots growing into crevices and exerting pressure, chemical reactions between rock minerals and slightly acidic water, the grinding action of glaciers in places where ice once covered the land. The process is geological in its slowness, measured in centuries and millennia, but it is continuous, always working to convert stone to soil. But minerals alone do not make soil. What transforms ground rock into true soil is the addition of organic matter. the accumulated residue of living things. Every leaf that falls, every twig that drops, every root that dies, every insect body, every piece of fungal tissue, all of this becomes part of the organic fraction of soil. And this organic matter does not simply accumulate, it is transformed through decomposition into humus, that dark, complex mixture of partially decomposed organic compounds that gives soil its color and many of its properties. Decomposition is the work of the soil community. It begins with the larger decomposers, beetles, millipedes, earthworms, that break down fallen leaves and wood into smaller pieces. A leaf falls intact in autumn, but within weeks it is fragmented, broken into pieces by the feeding of these organisms. The fragments are smaller, with more surface area, making them accessible to the next wave of decomposers. Fungi are the master decomposers of the forest. Their thread-like hyphae penetrate dead wood and leaf tissue, secreting enzymes that break down cellulose and lignin, the tough structural compounds that make up plant cell walls. Bacteria too play crucial roles, specializing in breaking down different compounds, some preferring simple sugars, others tackling more complex molecules. Together, fungi and bacteria transform dead organic matter into simpler compounds, releasing nutrients that were locked in tissue, making them available for uptake by plant roots. The process takes time. A fallen leaf might decompose completely in a year or two in a warm, moist environment. A fallen tree trunk might take decades or longer, its wood slowly softening, becoming spongy and friable, eventually crumbling into fragments indistinguishable from soil. The rate depends on many factors: temperature, moisture, the chemistry of the material being decomposed, the abundance and diversity of decomposers. But however long it takes, the transformation is inevitable. What was once living structure becomes, through decomposition, the substrate for new life. This process releases nutrients. Nitrogen, locked in proteins in living tissue, is released as the proteins are broken down by decomposers. Phosphorus, part of DNA and cell membranes, is liberated when cells disintegrate. Potassium, calcium, magnesium, all the minerals that were taken up from soil by the living plant are returned to the soil through decomposition, ready to be taken up again by new roots, cycling endlessly through the ecosystem. But not all organic matter decomposes quickly. Some of it is transformed into humus, a stable form of organic matter that resists further decomposition and can persist in soil for decades or centuries. Humus is dark, almost black, and it gives soil many of its beneficial properties. It holds water like a sponge, increasing the soil's water-holding capacity. It has a high cation exchange capacity, meaning it can hold on to positively charged nutrient ions and release them gradually to plant roots. It improves soil structure, binding mineral particles together into aggregates that create the porous, crumbly texture that characterizes healthy soil. The structure of soil is as important as its composition. In healthy forest soil, particles are not densely packed, but are organized into aggregates, small clumps of minerals and organic matter, bound together by fungal hyphae, bacterial secretions, and the sticky substances produced by roots. Between these aggregates are pore spaces, voids of various sizes that serve crucial functions. Large pores allow rapid drainage and provide pathways for roots to penetrate. Smaller pores hold water against gravity through capillary action, creating a reservoir that plants can draw upon between rain events. The balance of large and small pores determines how well soil drains and how much water it retains, a balance that is critical to plant health. Air occupies the pore spaces that are not filled with water. Roots need oxygen to respire, to power the metabolic processes that fuel growth and nutrient uptake. In waterlogged soil, where all pores are filled with water, roots suffocate, unable to obtain the oxygen they need. This is why soil structure matters. It creates the drainage that prevents waterlogging, maintains the air-filled pore space that roots require. The soil community extends far beyond decomposers. Predators hunt in the darkness of the soil. Predatory mites feeding on springtails, nematodes parasitizing bacteria or other nematodes, centipedes hunting any small creature they encounter. There are grazers, protozoa gliding through water films on soil particles, consuming bacteria and releasing nutrients in their waste. There are ecosystem engineers, earthworms that burrow through soil, creating permanent channels, mixing organic matter from the surface deep into the soil profile. Their waste products, castings, enriching soil fertility wherever they are deposited. Earthworms deserve special attention. In forests where they are abundant, a single acre might contain 1 million or more earthworms, collectively weighing hundreds of pounds. These worms ingest soil and organic matter, grind it in their gizzards, digest what they can, and excrete the rest as castings. Soil that has been mechanically broken down and enriched with nutrients from the worm's digestive secretions. Over the course of a year, earthworms can process tons of soil per acre, thoroughly mixing and reworking the upper soil layers, creating what Charles Darwin called vegetable mold, the rich topsoil that supports plant growth. The depth of soil varies greatly across the forest. In some places, soil may be many feet deep, the accumulated product of thousands of years of weathering and organic matter addition. In other places, bedrock lies close to the surface, and soil is shallow, just a few inches of organic rich material filling depressions in the rock. Trees adapt to these variations, their roots spreading widely in shallow soil to compensate for the limited depth, or plunging deeply where soil depth permits, always seeking the resources they need. Soil has layers, a vertical organization called the soil profile. At the surface is the O horizon, the organic layer, fresh and partially decomposed leaves and wood, the recent contributions of the forest community. Below this is the A horizon, or topsoil, dark with humus, rich in organic matter, the zone of greatest biological activity, where most roots concentrate. Below the topsoil comes the B horizon, or subsoil, lighter in color, less organic matter, but enriched with minerals leached from the layers above. And below that, eventually, is the C horizon, weathering bedrock, the parent material from which the mineral component of soil ultimately derives. This layering develops over time, the product of water moving downward through the profile, carrying dissolved substances, redepositing them in lower layers. It is a slow stratification, but a real one, creating vertical differentiation in what was once more uniform material. The chemistry of soil is complex. The pH, the measure of acidity or alkalinity, affects nutrient availability and influences which plants can thrive. Most forest soils are slightly acidic, a result of organic acids released during decomposition and the absence of limestone or other alkaline materials. Some nutrients are more available in acidic soils, others in alkaline. Plants have adapted to the pH of their native soils, and disturbances that alter pH can have profound effects on forest composition. Nutrients exist in soil in various forms, some dissolved in soil water and immediately available to roots, others bound to soil particles or locked in organic matter and only slowly released. The total amount of a nutrient in soil may be large, but what matters to plants is the available fraction, the portion that roots can actually absorb. This is where the soil community is crucial. Through decomposition, mineralization, and chemical transformation, the community converts nutrients from unavailable to available forms, regulating the supply that supports plant growth. Mycorrhizal fungi, which we have mentioned before in connection with roots, are particularly important in nutrient uptake. The fungal hyphae extend far beyond the root zone, exploring volumes of soil that roots alone could never access. They are especially important for phosphorus acquisition. Phosphorus is relatively immobile in soil, so the ability of mycorrhizal fungi to reach out and gather it from a large area is critical to tree nutrition. In return for this service, the tree supplies the fungi with sugars, maintaining the partnership that benefits both. The temperature of soil affects all biological processes within it. Warmer soil supports faster decomposition, more rapid nutrient cycling, more active root growth. Colder soil slows everything down. The forest floor, shaded by the canopy, remains cooler than open ground, and this coolness affects soil processes. Decomposition is slower in cool forest soil than in warm, open soil, which is one reason why organic matter accumulates to greater depths in forests. It is added faster than it can fully decompose, creating the thick O-horizons characteristic of undisturbed forest floors. Moisture is equally critical. Soil that is too dry limits microbial activity, slows decomposition, stresses plant roots. Soil that is too wet excludes air, suffocates roots, favors only those organisms adapted to anaerobic conditions. The ideal is soil that is moist but well drained, where water is available but does not exclude air, where biological activity can proceed at optimal rates. Forest soils, with their high organic matter content and good structure, generally maintain this ideal balance better than more disturbed soils. The age of soil varies as much as its depth. In recently glaciated landscapes, soil is young, still developing, still accumulating organic matter and developing structure. In landscapes that have been stable for millions of years, soil is ancient, deeply weathered, often leached of nutrients, the product of such prolonged weathering that the most soluble minerals have long since been removed. Young soils tend to be more fertile. Old soils, paradoxically, can be nutrient poor despite their great age. Disturbance resets soil development. If erosion removes topsoil, the process begins again from a point much earlier in the sequence. If cultivation mixes and aerates soil, organic matter decomposes more rapidly, and the characteristics built up over centuries can be lost in decades. Forest soil, protected by its canopy, stabilized by roots, accumulating organic matter continuously, represents a mature state, a balance achieved between inputs and losses, between accumulation and transformation. Take another handful of this soil, hold it and consider what you are holding. The ground-up substance of stone, the transformed remains of countless organisms, the dwelling place of billions of living beings, the foundation of the forest's productivity, the medium through which water moves and roots extend and nutrients cycle. It is easy to overlook soil, to take it for granted, to think of it as mere background. But without soil, there is no forest. Without soil, there is no terrestrial life as we know it. The soil beneath you is ancient and young simultaneously. Ancient in the bedrock from which its minerals derive, young in the constant renewal of its organic fraction, in the ongoing work of decomposition and transformation. It is stable and dynamic, stable in its persistence, dynamic in its constant internal turnover, its ceaseless biochemical and biological activity. Let the soil fall from your fingers back to the ground, back to where it belongs. It will be incorporated by the next rain, by the movements of worms and roots, back into the matrix from which you briefly borrowed it. And there it will continue its work, supporting, nourishing, processing, being the foundation that holds everything else up, literally and figuratively, the composure at the base of all this vertical reaching, this upward growth, this forest that rises from earth towards sky, but never forgets its origin, its dependence, its debt to the dark ground below. This is the composure of soil, steady, essential, alive in ways both obvious and hidden. The ground of all that grows, the foundation of the forest's peace. The light here is different. You have been walking in this forest long enough now to forget what full sunlight feels like, what it means to stand in the open with the sun's direct rays on your face and shoulders. Here, beneath the canopy, the light is transformed, softened, filtered, reduced to a gentle glow that seems to come from everywhere and nowhere at once. This is the realm of shade. And shade brings with it a particular kind of stillness, a quietness that is as much about the quality of light as it is about sound. Look upward through the layers of leaves. The canopy is dense here, the overlapping crowns of multiple trees, creating a ceiling that intercepts most of the light falling from the sky. What sunlight does penetrate arrives transformed, having passed through leaf after leaf, each one absorbing certain wavelengths, particularly the reds and blues that chlorophyll uses most efficiently for photosynthesis. The light that reaches you is enriched in green wavelengths, the colors that leaves reflect rather than absorb, giving the illumination its characteristic tint, as if you are seeing the world through a filter of living green. The intensity of light here is perhaps 1% of what falls on the canopy above, sometimes even less. It is difficult to comprehend how little light this represents. So little that the human eye, adaptable as it is, must widen its pupils, must become more sensitive to see clearly in this dimness. Yet plants live here, grow here, photosynthesize here, on this meager allowance of light. They are specialists, these shade-adapted species, ferns and seedlings, and ground-level herbs that have evolved to capture and use every photon that reaches them, to construct their tissues on an energy budget that would starve sun-loving plants. The quality of stillness that shade creates is partly about the absence of harsh contrasts. In direct sunlight, shadows are sharp-edged, dark, creating a landscape of extremes, blazing highlights and deep shadows with little transition between them. But in the forest's shade, there are no sharp shadows. The light is so diffuse, coming from so many directions after its multiple reflections and transmissions through leaves, that objects cast only the faintest shadows, if any at all. Everything exists in a kind of gentle twilight, where forms are visible but softened, where colors are muted, where the visual harshness of full sun is replaced by a restful uniformity. This uniformity affects how you perceive the passage of time. In open landscapes, the sun's movement across the sky is obvious. Shadows wheel around. The angle of light changes dramatically from morning to afternoon. The quality of illumination shifts from the cool tones of morning to the warm gold of evening. But here, beneath the canopy, these changes are subtle to the point of imperceptibility. The shade remains shade, the light dim and green, whether it is 9 in the morning or 3 in the afternoon. Time seems to slow, to become less urgent, when its visible markers are so muted. The temperature, too, is affected by shade. On a hot summer day, the open ground can become scorching, the soil surface reaching temperatures that would burn unprotected skin. But the forest floor remains cool, protected by the canopy's insulation. The leaves above absorb and re-radiate heat, preventing it from reaching the ground. The transpiration of water from leaf surfaces, gallons and gallons evaporating from a single large tree, creates a cooling effect, lowering the temperature of the air within the canopy. The result is a microclimate significantly cooler than the world outside the forest, a refuge from heat, a demonstration of the forest's capacity to modify its own environment. The stillness of the air is partly a product of this shade as well. Wind is driven by temperature differences, warm air rising, cool air flowing in to replace it, creating circulation. But in the forest, where temperatures are moderated, where the canopy dampens temperature extremes, the driving force for wind is reduced. The canopy itself also acts as a windbreak, intercepting moving air, breaking it into smaller eddies and currents, slowing its speed. By the time air reaches the forest floor, it is barely moving, just the gentlest breath, enough to be felt, but not strong enough to disturb the fallen leaves or bend the ferns. Stand very still and feel this absence of wind. The air is so calm that you become aware of your own breath as a disturbance, your own movement as an intrusion into the stillness. The forest is not holding its breath. It is simply that this is its natural state, calm, unruffled, patient. The drama of weather, the rush of storms, happen above, at canopy height and beyond. Down here, you are sheltered, protected, held in a space that weather touches only gently. The shade affects what can grow here. Only plants that can photosynthesize efficiently at low light levels survive on the forest floor. Many tree seedlings begin life here, small saplings a few inches or a few feet tall, waiting. They are waiting for a gap, for an opening in the canopy created by the fall of an old tree or the loss of a major branch. When such a gap appears, light suddenly floods down to the forest floor, and the waiting seedlings race upward, competing to be the one that fills the gap, that reaches the canopy and claims that space for itself. But until that gap appears, they wait, growing slowly, adding perhaps just an inch or two of height per year, maintaining themselves on the minimal light available, patient beyond human comprehension. Some plants have given up on reaching the canopy and have specialized in life in perpetual shade. Ferns are masters of this niche, their delicate fronds adapted to capture the diffuse light efficiently. The fronds are often deeply divided, creating large surface areas for light capture relative to the plant's investment in structural tissue. They are positioned horizontally, perpendicular to the light falling from above, maximizing interception. And they are thin, allowing the light that does penetrate to reach the chloroplasts within without being absorbed by thick, light-blocking tissues. Mosses, which we explored in an earlier chapter, are also shade specialists. They require so little light that they can grow on surfaces, tree, trunks, rocks, where higher plants cannot establish themselves. Their position often places them in even deeper shade than the forest floor, yet they persist, conducting photosynthesis at rates that would be undetectable in most plants, but that are sufficient for their slow growth. The color of plants in deep shade is often a darker green than plants growing in sun. This darker color indicates a higher concentration of chlorophyll, more of the light-capturing pigment packed into each cell, compensating for the lower light levels by increasing the plant's ability to capture what little light is available. It is an adaptation made visible, a response to environmental conditions written in the saturation of green. The stillness of shade is also a stillness of reduced competition, of a slower pace of life. In the sun-drenched meadow or forest edge, plants race to grow, to overtop their neighbors, to claim light before someone else does. Growth is fast, competition fierce, and lifespans are often short. Annual plants completing their entire life cycle in a single season, living fast and dying young. But here, in the shade, the pace is different. Growth is slow because resources are limited, but this slowness brings its own benefits. Slow growth produces dense wood, tissues that are more resistant to decay, structures that can last for years rather than months. The insects that live in shade are often different from those in sun. Many shade-dwelling insects are darker in color, absorbing more of the limited light and heat available. They move more slowly, their metabolism adjusted to the cooler temperatures of the forest floor. Some spend most of their time hidden in leaf litter or under bark, emerging only to feed or reproduce, living cryptic lives in a cryptic environment. Listen to the sound of shade. It is not silent. There is no true silence in nature, but it is quiet. The sounds are small, intimate, close. The rustling of a small mammal moving through leaf litter, the soft call of a bird somewhere in the mid-canopy, the almost imperceptible sound of water dripping from leaves after rain, a process that continues for hours after the rain itself has stopped. These sounds do not carry far. They are absorbed by the forest, by the soft surfaces of leaves and moss and humus, by the countless small barriers to sound waves that the forest's structure creates. Shade creates a different relationship with time and season. In the sun, the seasons are dramatic, the arc of the sun changing significantly between summer and winter, the intensity of light varying enormously, the temperature swings extreme. But in the forest, seasonal changes are muted. Winter is darker than summer, yes, but the shade was already deep, so the change is less dramatic. Temperature changes are moderated by the canopy in summer and by the insulation of soil and litter in winter. The forest experiences the seasons, but more gently, with less violence, with transitions that are gradual rather than sudden. There is a psychological effect to being in shade for extended periods. The reduced light levels calm the nervous system, lower heart rate, reduce the stress hormones that bright light and heat can trigger. Humans evolved in environments with trees, with shelter, with places of refuge from the sun's intensity. Some part of our biology still responds to shade as safety, as home, as the kind of place where we can rest without vigilance. This is why forests feel peaceful, why time spent under the canopy is restorative. It is not merely aesthetic, but physiological, a response written into our evolutionary history. The shade you are experiencing now has been created by the work of decades or centuries. The trees that form this canopy took years to grow to their current height, added ring upon ring, extended branch after branch, until their crowns met and overlapped, creating this continuous ceiling. The shade is not an accident, but a consequence of patient growth, of many trees succeeding in their individual quests for light, and in doing so, creating, collectively, this shaded understory where different rules apply, where different organisms thrive. The stillness of shade is not emptiness. It is not the absence of activity, but the presence of a different kind of activity, slower, quieter, more subtle. It is the ferns slowly unfurling new fronds. It is the moss imperceptibly expanding across a log. It is the tree seedling adding microscopic increments to its height. It is the soil organisms processing organic matter at rates measured in months and years rather than days. All of this is happening around you, constantly, but at a pace that requires patience to observe, that reveals itself only to those willing to slow down, to match their own rhythms to the forest's. Close your eyes for a moment. With vision removed, the other senses become more acute. You feel the coolness of the shaded air on your skin. You smell the earthy scent of humus, the green scent of living leaves. You hear the small sounds amplified, sounds that were there all along, but that your eye's dominance suppressed. Without the visual input, the forest reveals itself as a symphony of subtle sensations, each one quiet, but together creating a rich sensory environment. Open your eyes again. The shade is still there, the green filtered light, the soft illumination that knows no harsh edges. You are seeing the forest's secret interior, the place that exists beneath the bright crown visible from outside, the place where life proceeds at its own pace, unbothered by the sun's demands, sheltered by the very structures that reach up to capture sunlight above. This is the stillness of shade, protective, gentle, timeless. It is the forest's gift to itself and to those who enter. The creation of a space where intensity is lowered, where harshness is filtered away, where life can proceed slowly and thoroughly, building structures meant to last, creating communities woven together by time and patience. The shade will remain after you leave. It was here before you arrived. It will be here tomorrow, and next year, and decades from now, maintained by the trees, recreated each spring when leaves unfurl, deepened by the forest's continued growth. The stillness persisting like a promise, like a refuge, like the forest's own quiet heart. Time moves differently in the forest than in the human world of clocks and calendars. Here, time is measured not in hours and minutes, but in cycles. The cycle of day and night, the cycle of wet and dry, and most profoundly, the cycle of seasons. The turning of seasons is the forest's great rhythm, the pulse that governs when leaves emerge and when they fall, when growth accelerates and when it pauses, when life expands and when it contracts into patient waiting. We are in the fullness of summer now, or perhaps the generous days of late spring, a time when the forest is at its most abundant, its most green, its most alive in the visible sense. The canopy is complete, every tree clothed in its full complement of leaves. The understory is lush with ferns and shade-loving herbs. The forest floor is soft with moisture, the soil rich and active. This is the season of growth, of photosynthesis at its maximum, of energy capture and transformation, of the forest building itself day by day. But this abundance is not permanent. It is one phase in a cycle that turns inevitably, that brings change as certain as the orbit of the Earth around the Sun. Let us walk through this cycle together, beginning where we are now and moving forward through the year, witnessing the transformations that each season brings to these trees, to this forest, to the intricate web of life that exists here. Summer is the season of fullness. The days are long, the sun's arc across the sky high and extended, providing many hours of light for photosynthesis. The trees are working at their maximum capacity, their leaves capturing sunlight and converting it into sugars, their roots drawing water and nutrients from soil warmed to optimal temperatures for biological activity. Growth is rapid now. New wood is being added to trunks and branches. New roots are extending into the soil. The annual increment that will become this year's growth ring is forming, wider than it will be in less favorable years. The forest canopy is a factory of oxygen production. All those millions of leaves, all conducting photosynthesis simultaneously, are releasing oxygen into the atmosphere at rates that measurably enrich the air. This is why forests are called the lungs of the earth, not because they breathe in the way animals do, but because they participate in the gas exchange that maintains atmospheric composition, removing carbon dioxide and releasing oxygen in a process that has been sustaining life on this planet for hundreds of millions of years. But even now, in the height of abundance, there are signs of the changes to come. Some leaves at the top of the canopy, the oldest ones that emerged first in spring, are beginning to show their age. They are slightly duller in color, their edges perhaps torn by wind or nibbled by insects. They have been photosynthesizing for months now, and while they are still functional, their efficiency is declining. The tree will eventually replace them, but for now they continue working, extracting what productivity they can from the remaining weeks of the growing season. As summer progresses toward autumn, the changes become more noticeable. The days begin to shorten. The sun's arc across the sky begins to lower. The angle of light striking the canopy becomes more oblique, spreading the same amount of solar energy over a larger area, reducing intensity. These changes are subtle at first. Minutes of daylight lost each day, slight shifts in sun angle, but the trees sense them. Day length, not temperature, is the primary signal that triggers the tree's preparation for winter. Autumn's arrival is gradual, then sudden. There comes a point, usually after the first significant cold spell or after a threshold of day length has been passed, when the forest begins its transformation. The trees start withdrawing resources from their leaves, breaking down proteins and chlorophyll, transporting the valuable nitrogen and other nutrients back into the branches and trunk for storage over winter. This nutrient withdrawal is why leaves change color. As the green chlorophyll disappears, the other pigments that were always present become visible. The yellows and oranges of autumn leaves come from carotenoid pigments that were masked by chlorophyll during the growing season. These pigments, which assist in photosynthesis by capturing wavelengths of light that chlorophyll cannot, now reveal themselves as the chlorophyll breaks down. The reds and purples come from anthocyanins, pigments that some trees produce in autumn, perhaps to protect the leaves during the final phase of nutrient withdrawal, or perhaps as a byproduct of sugar accumulation in leaves as the connection between leaf and branch begins to close. The display of autumn color is glorious, but brief. For a few weeks, the forest becomes a tapestry of golds and reds, oranges and purples, mixed with the evergreen's persistent dark greens and the browns of leaves that have finished their transformation. The canopy becomes a celebration of color, each tree contributing its particular shade to the collective display. Sunlight, angling through this colored canopy, takes on warm tones, creating a golden quality to the light that is unique to this season. But this beauty is preparation for loss. As nutrient withdrawal completes, each leaf develops an abscission layer at the base of its stem, a layer of cells that will separate, breaking the connection between leaf and tree. When this layer is complete, the leaf is held only by the vascular connections, and these are easily broken. A gust of wind, a rainstorm, the leaf's own weight. Any of these can now cause it to fall. The falling of leaves is one of the forest's great events, though it happens silently, each leaf descending on its own, spinning slowly as it falls, landing softly on the forest floor. But multiply this by millions of leaves, by all the deciduous trees in the forest, and the cumulative effect is dramatic. Over the course of a few weeks, the entire canopy is transformed from full and opaque to bare and transparent. The forest opens up visually, revealing structures that were hidden during the leafy months. The architecture of branches, the patterns of trunks, the shape of the forest itself. The fallen leaves carpet the ground, creating a new layer in the litter, beginning their transformation from living tissue to soil. They are food for the decomposers, raw material for next year's growth, part of the endless cycle of death and renewal that characterizes all ecosystems. But that is especially visible in deciduous forests, where the cycle is seasonal and dramatic. With the leaves gone, the trees enter dormancy. This is not sleep. The trees are not unconscious, but it is a state of minimal activity, a conservation of resources during the months when conditions do not favor growth. The metabolism slows, the transport of water and nutrients reduces to a trickle. Growth ceases entirely. The buds that will become next year's leaves and flowers are already formed, protected by overlapping scales, waiting for spring. Inside the twigs and branches and trunk, the cambium is dormant, the cells paused in their division, time suspended until warmth returns. Winter in a temperate forest is a study in patience. The bare branches create a different kind of beauty, stark, structural, honest. The essential form of each tree is revealed without the softening effect of leaves. You can see how the trunk divides, how the branches angle and taper, how the silhouette is characteristic of the species. Even without leaves, an oak looks different from a maple, an ash different from a hickory. The forest is quieter in winter, though not silent. The sounds of insects are largely absent. Most have died or entered their own forms of dormancy, eggs or pupae waiting for spring. Many birds have migrated, leaving only the year-round residents, species adapted to survive on the winter's sparse offerings. Mammals are still active, some of them, their tracks visible in snow if snow has fallen, signs of their passage through the sleeping forest. Snow transforms the forest when it comes. It covers the ground, softens the angularity, creates a blanket of white that reflects what little light filters through the bare canopy. Snow accumulates on horizontal branches, weighs them down, sometimes breaks them if the load is too heavy or if the snow becomes ice. But mostly, snow is simply insulation, protecting the soil and the organisms within it from the worst extremes of cold, moderating temperature fluctuations, slowly melting to provide water when spring arrives. The cold of winter is significant. Temperatures fall below freezing, sometimes far below, and the trees must survive this without damage to their living tissues. The strategies vary by species. Some trees tolerate freezing in their xylem vessels, the water turning to ice, but the cells structured in ways that prevent rupture. Others maintain supercooled water in their cells, preventing ice formation through various biochemical means. Still others, particularly evergreens, have adapted their physiology to function at very low temperatures, conducting minimal photosynthesis even in winter, maintaining readiness for whenever conditions improve. The evergreens, pines, firs, spruces, and their relatives do not participate in the autumn display or the winter bareness. Their needles persist year-round, dark green constants in a landscape of seasonal change. These needles are adapted to survive winter, tough, waxy, resistant to water loss, able to tolerate freezing and thawing without damage. The trees remain capable of photosynthesis whenever temperatures rise above freezing and light is available, though their productivity in winter is minimal, just enough to maintain themselves. As winter progresses towards spring, the changes are at first imperceptible. The days lengthen, slowly at first, then more rapidly as the spring equinox approaches. The sun's arc across the sky begins to rise, the angle of light becoming less oblique, more direct. Temperatures fluctuate. Cold days still occur, but warm days become more frequent, and the soil begins to thaw, allowing water to move again, bringing life back to the frozen layers. Spring's arrival is tentative, a series of false starts and retreats before the season truly establishes itself. The buds on the trees swell, responding to increasing day length and warming temperatures. Inside each bud, the miniature leaves and flowers that were formed last summer and protected through winter begin to expand, preparing for their emergence. And then, on a day that seems no different from the one before it, the buds begin to open. The process is quick. Once started, leaves unfurl in a matter of days. The forest, which was bare and brown, suddenly tints green as millions of new leaves emerge, small at first, but expanding rapidly, reaching their full size within a week or two. This is one of the fastest transformations the forest undergoes, the flip from winter bareness to spring verdure happening almost too quickly to follow. The fresh leaves of spring are a different green than summer leaves, lighter, brighter, almost translucent when backlit. They are tender, not yet toughened by exposure, not yet darkened by the accumulation of chlorophyll to maximum concentrations. They are delicate and vulnerable, susceptible to frost, to insect damage, to desiccation, but they are also incredibly productive, conducting photosynthesis at high rates, taking advantage of the favorable conditions, long days, moderate temperatures, abundant moisture, to capture as much energy as possible. Spring is a time of acceleration. Everything that was paused resumes. The cambium begins dividing, adding new wood and new phloem. Roots extend, exploring soil, seeking nutrients and water. Flowers bloom. Many trees flower before or just as their leaves emerge, taking advantage of the brief period when pollinators are active, but competition from other flowers is minimal. The forest hums with activity, with insects awakening, birds returning from migration, mammals emerging from dens, all responding to the abundance that spring represents. And then, imperceptibly, spring transitions into summer and the cycle is complete. The leaves that emerged tender and light have matured into the full, dark green of photosynthetic maturity. The forest canopy has closed again, creating the shade and shelter that define the summer forest. Growth continues, but at a steadier pace, the explosive expansion of spring giving way to the sustained productivity of summer. This cycle, summer's fullness, autumn's preparation, winter's dormancy, spring's renewal, repeats year after year, decade after decade, century after century. Individual trees may live through dozens or hundreds of cycles, each year adding one more ring to their record, one more set of memories written in wood. Some trees were saplings when this cycle began a century ago and are now towering elders. Others were seeds that fell just years ago and are now saplings themselves, beginning their own journey through the seasons. The turning of seasons is not merely a backdrop to the forest's life, but an integral part of it. The forest is shaped by this cycling, adapted to it, dependent on it. The deciduous strategy, growing leaves in the favorable season, shedding them when conditions worsen, is an elegant solution to the challenge of surviving in an environment where resources vary seasonally. The energy cost of growing new leaves each spring is more than repaid by the ability to avoid the costs of maintaining them through the harsh winter. Stand here in this moment, in this season, and imagine the forest as it will be in 6 months, in a year, in 10 years. The turning continues, patient and inexorable, the great wheel of the seasons, moving the forest through its phases, each phase necessary, each contributing to the whole. There is wisdom in this cycling, in this acceptance of change, in this willingness to let go when the time for letting go arrives, and to begin again when the time for beginning returns. This is the turning of seasons, predictable yet always slightly different, ancient yet eternally renewing. The forest's participation in the planetary rhythms that govern all life, the evidence written in rings and leaves, and the patient endurance of trees that what changes most profoundly is also what remains most constant. The day is progressing, the sun slowly drifting westward. The light is softening, the forest taking on a different quality. Night is approaching, and with it, another world awakens. Darkness descends gradually. The diurnal birds have fallen silent, yielding their territory to nocturnal creatures. An owl calls in the distance, soft and mysterious. Bat wings flutter through the air, invisible but felt. The sounds of night are different from day, more sparse, more meaningful, small notes inscribed into deep silence. Your eyes can see very little now, but your other senses sharpen. The forest's scent is more intense, moist earth, green leaves, decaying wood. Coolness on your skin, your breathing has slowed, synchronized with the forest's nocturnal rhythm. Darkness offers privacy, concealment, protection, withdrawal from the world. You cannot see the trees now, but you know they are there, silent guardians, standing with the same patience through night and day. Dawn breaks slowly. With the first light, you begin to see the forest's hidden geometry. Each tree's branching pattern is a fractal. The main trunk divides into major branches, these into smaller branches, these into even smaller ones, the same pattern repeating at every scale. Look at a fern frond, a central stem with leaflets branching off, each leaflet subdivided again. The same pattern, different scales. It's the same in roots, in leaf veins, in river networks. Nature uses this geometry because it's efficient, maximum surface area with minimum material. These patterns aren't just beautiful, they're functional. By branching this way, the tree can spread millions of leaves through space, capturing maximum light with a minimal skeleton. Everything is connected, everything serves a purpose, mathematics and life intertwined. Every tree is an archive. The rings in its trunk don't just show age, each ring tells that year's story. Wide rings indicate good years, narrow ones mark drought and hardship. Fire scars, insect attacks, storm damage, all are preserved in wood, a permanent and honest record. Wood's memory is unconscious but absolute, unchangeable, uneditable. The tree carries its past within, in every cell, in every fiber. Scientists can read this memory to decode the climate, events, and changes of centuries past. Hold a piece of wood in your hand. This wood was perhaps formed 100 years ago and has remained unchanged since then. Within it are solar energy, minerals from soil, isotopes from that year's rain. Wood remembers, not for itself, but simply because it exists, as permanent testimony. Birds are singing, each in its own layer, some at the top, some in the middle, some on the ground. Each species has found its niche, living in the same forest, but in different worlds. Woodpeckers drum rhythmically, nuthatches walk down trunks, owls hunt silently. The wind returns, rustling leaves, swaying branches. Wind caresses the forest, touching every surface, carrying scents, dispersing sounds. Trees bend with the wind, without resistance yet unbreaking, finding strength in flexibility. Then the wind dies and silence returns. But this silence is not emptiness. There is texture, there is depth. Small sounds, a leaf falling, an insect moving, a distant bird calling. Silence is an architecture, built with absorbent surfaces, soft soil, the trees themselves, constructed to absorb sound and offer peace. Look at the forest floor. Seeds are everywhere. Oak acorns, winged maple seeds, pine cones. Each seed is potential, a future tree, a package of genetic information and stored energy. Trees produce thousands of seeds. Most will fail. But this isn't waste, it's strategy. Overwhelming odds with numbers, ensuring a few survive. A seed falls to earth, waits, germinates when conditions are right. First the root descends, then the shoot rises, reaching toward light. Most seedlings die in their first year. Herbivores, competition, drought, shade. But some survive, waiting years patiently, growing slowly, one day reaching the canopy. And there, when mature, they begin producing their own seeds. The cycle continues. This is the eternal return, repetition with variation. Each spring is new, yet carries the legacy of all springs. Each tree is unique, yet continues its ancestors. The forest changes but remains. Individuals die, but the community persists. Seasons turn, rings form, seeds fall. Seedlings emerge, trees grow, age, die, decay, and transform into new life. Forever. Carbon, water, energy remain in the cycle, changing form but never disappearing. The sun is setting now. The time to leave the forest approaches. But the forest will remain here. Tomorrow, next week, next year, next century. Trees will continue standing, roots growing, leaves photosynthesizing, seeds falling. You have changed. You are slower, quieter, carrying the forest's peace within you. And perhaps one day you will return, and the forest will be here again, waiting for you, ready to offer new secrets. The forest is a teacher of patience, resilience, the wisdom of cycles. It doesn't hurry, doesn't complain, simply exists and grows and lives. And in doing so, it gives us life's deepest lessons. Slowness is strength. Silence has value. Every ending is a new beginning. The secret life of trees, a journey into silence, ends here. But in truth, nothing ends. It only transforms, continues, passes into the next turn of the eternal return. Go in peace. The forest will always be here. If you are still awake, that is perfectly fine. And if you have already drifted into sleep, then let the quiet carry you gently onward. There is no ending here, only rest. Good night.